Thank you everyone for being here, and special thank you to the organizers for invitation and planning this amazing event in such a short time. So I'll be talking about foundation models for robotics. First of all, let me clarify foundation models versus LLMs, large language models. Okay, so originally these terms were different, but they are used interchangeably these days. So foundation models are general purpose AI models that can be adapted to different kind of domains or situations. LLMs have to do with language, right? But they are used interchangeably, fortunately or unfortunately. I'm not sure. So I'll also be using these terms interchangeably during my talk. So whenever I say LLM, just imagine foundation model. I'll cover robotics plus foundation model, like what's my motivation and how do we do robotics in post LLM era and after LLM era. What are the evolving trends? And then I'll talk about how do we improve large language models in general. And of course, they also help robotics in that. A little bit about me. So I did PhD from Hokkaido University in Japan. And most of my research on robotics and reinforcement learning happened during when I was managing a team in Tokyo Research at IBM. And then I became program director for neurosymbolic AI, and I moved to IBM Watson Research in New York. So although I work with a lot with large language models and reasoning in large language models, at the back of my mind, it's always like, how does it apply to robotics? What's my main motivation? Like, why do I like robots? Why do I work in this area towards better robotics? So it has to do, like, when I remember when I was a child, like 6 years old, my father, who is also a computer scientist, he used to tell me that within 10 to 15 years, we'll have robot helpers in our home. Okay? And they will do all our like tasks that we do around the house, making our bed sheet, picking up the stuff from the ground and cleaning the house. And I used to do all these chores, and I used to think that it's only for 10 years. When I'll grow up, I'll just get one of these and I don't have to do that anymore. Okay. But after 30 years now, these are the best robots we have in our home. Okay. So there is a huge gap between what maybe I was too naive to think that we'll get something like that in our home. But there is a huge gap here, right? And how do we fill this gap? I know, like most of the people here, you must know about large language models. But just to give a very quick like introduction to LLMs, what LLMs are, but they are not. It basically started from this paper, Attention is All You Need. And the title of the paper is very catchy, but there is a lot of history to why attention is all you need. Like there was a lot of other things that people were using before, but then they came out with this transformer architecture. And this is the architecture that is used by most of the models that we see. So just a little bit about attention. So attention just means that we allow the model to focus on a part of input when it's generating an output. So in case of self-attention, for example, on the left-hand side, the animal didn't cross the street because it was too tired. So here it refers to the animal. In the second sentence, it was too wide. Here it refers to the street, right? So this is what attention allows us to do. And similarly, when we convert images into titles, we do the same thing. When it's focusing on, when it's generating the word dog, it focuses at the part of the image that contains the dog. So LLMs are basically next token predictors. For simplicity, let's assume they are next word predictors. Okay. So if I ask what is the capital of Japan, it will say Tokyo. Okay. So, or we hope that it will say Tokyo. So it encodes our input into some kind of embedding space, and then it decodes it and it generates the next word. So that's what they're doing all the time. A little bit looking into the encoder. Of course, we can have like architecture where we have only encoder, only decoder, and different kind of combination of that. So these consist of many self-attention modules, and in self-attention modules, intuitively, it's very easy to understand. We have query, key, and value. Query is like the question that we want to ask. Key is like, you can imagine, it's the field name, and value is the value that we want to retrieve. Okay. So if given that table, so you can see query is what's the full name, key can be name field, and value can be my name. So how they become query key value, we train them to be like that. Okay, so we train these matrices WQ, WA, and WV. Again, it's oversimplification. There is actually multi-headed attention. There is cascading of these attention modules. There are other positional embeddings. There are other stuff that I'm ignoring here. But basically, it's this self-attention is the main innovation here. From here, let me go to foundation model for robotics. In my opinion, the biggest contribution of large language models is that it did for natural language understanding what convolutional neural networks did for vision, computer vision, and perception. Okay. So before that, I remember, like, before large language models came into the picture, it was very difficult, especially for a non-NLP person, to use natural language in any constructive way. I still strongly believe LLMs are a piece of the puzzle. They are not the full solution. They will never be the full solution in their current form. They suffer from very serious shortcomings also. They have very high computational cost. They need fine tuning in many applications. There is like the issue of real time operation versus the model size. The bigger the model, the better. But then again, you compromise on the real time performance and reliability. You always hope they are doing what they are supposed to do, but you are never sure. That's why I say, like, robotics still remain the ultimate application of AI. Although now there are, in the news article, some people claim LLMs are AGI and stuff like that. I don't know why they do that. But anyways, so LLMs are not the final frontier for sure. Here I want to show you a video, like it will be a kind of 2-minute video. This is a work that we did back in 2017, where we were developing a robotics framework, kind of middleware for orchestration of high-level reasoning and converting them into robot commands. So I'll show a video and then I'll talk a bit more about it. It will have, yeah, it has some, but it's okay if the sound doesn't go. Okay. No, it just started from this. So here, what we are doing is we have two robots. One is the manipulator robot. The other one has some sensors on it. It's a communication robot. So I'm telling the robot, this robot, which is Pepper robot, to learn a task and then execute that task, like teach that task to another robot. with a very different form. Okay. There are some skills, for example, perception is the skill. This robot can do manipulation. This robot is very poor in manipulation. So it tells another robot how to do that. So I'm teaching a task called peg assembly task, where we already the robot has learned the skill on how to put a peg into the hole, and then this robot will use that low level skill to teach it to the other robot. So it learns the task, it finds like I have inserted few pegs in few holes, which peg in which hole, it have learned that, and now it tries to execute that on another robot. Okay. So this peg assembly task, now the sensing part of it, like where to move the robot in order to insert the peg, this is a task that was learned separately, and this is a skill that was learned separately, and this skill is used to perform this overall scenario. And this continues. So one of the biggest issue at that time was that how to convert human conversation into something that the robot understands and it can perform at very low level. So we kept this communication very template based. Okay, so in a way you have to become a robot to communicate with the robot. Okay, so you cannot communicate in natural language. At least it was not possible at that time with simple. So it was a whole research topic, how to make it communicate in more natural language. How would I do it today? If someone asked me to repeat this project and do it today, I think I would go for LLM agents, maybe SECAN kind of architecture. Okay. So there are more options now than they were available in 2017. So for example, in SECAN, we know that the individual skills are they are pre-trained, and there are value functions available for those pre-trained skills. And then LLMs basically help convert our natural language conversation into like the possible instructions. Okay, so they have this common sense knowledge of the world, and they convert it into possible instructions. And then we use the value functions to find which one is most likely here or the best action here. And we do that. For example, here, I spilled my drink, can you help? So you very natural conversation. And the LLM, again, we hope that they will give us some solution, like find a cleaner, find a sponge, and then we have the value functions, and then we can pick up the best one, and we go on. And if you look at one of the things that's really attractive about LLMs is they're so easy to use, and that's why people think that they solve everything because they're very easy to deal with, right? So if you're not training them, so LLM prompts. So this is how we do it. So we just give I would and one, and then we ask the LLM to generate something. Then we go to the next. We put the first action, and then we ask for the second action. We prompt for the second action. As we know, LLMs are next token predictors, so they predict whatever they want to. So this is what I was saying. Like we post LLM, we have a lot more tools available now. Okay. Again, they are not the solution, the final solution, but we have a very strong tool in our repository that was not available before. But the issue is, can we trust an LLM? Okay, can we trust them without any guardrails, without anything around them? This is a video. It's not related to LLMs by any means, but this is what we did. Can we play this? This is a paper we submitted in 2018 ICRA, and this is where we are teaching reinforcement learning to robot from scratch. Okay, and the kind of actions that the robot do, they are very dangerous. Like some kind of AI, for example, you can do simulations even in real environment. But with robots, you don't want to mess up. Like one wrong action, robot breaks down, and it costs a lot. It takes a lot of time, and so. But we know LLMs are next token predictors. They don't possess a world model. They don't have the abstraction of the task that we humans do. So when we humans start talking, we usually have the answer. We just try to communicate that. Okay. LLMs don't have the answer before they start creating these tokens. Okay, so they don't know the final answer. So, that's the issue. They don't solve the problem in the way that humans do. And similarly, like the algorithm is complex or not doesn't matter for LLM. They just start generating the tokens. Okay, it can be a simple algorithm. It can be complicated. Doesn't matter to them. So there are a lot of limitations. So we cannot trust LLMs right now. In future, in this form, in this architecture, we'll never be able to do that. So we need something around that. I'll talk a little bit about how we can improve LLM. But whatever we say, like we like LLMs or we don't like LLM, we are believers or non-believers in this case. So world is going towards this direction. Okay, so we have this planning, actuation, perception loop given the goal. We see this kind of research also where everything is LLM. Okay, and we see this kind of where we replace individual components with the models. For example, in this case, there are papers that do planning using LLM, or LLM converts natural language into some planning language, and they use external tool for planning, and then code models to control the robot, and sensor models to basically sense what the robot is doing. An example, just as an example, this is a research that I found interesting, and one of the reasons was it came very early days of LLMs after ChatGPT, so that's why I liked it. So here you see there is a multimodal kind of large language model, and it is doing both visual encoding and at the same time text tokenization, text encoding also. So the same model can basically take a low level like video, and then it can generate the next control signals for the car. And you can also talk with that model. You can ask it, why did you do something? And it will tell you why I took some action. Whether that explanation and that control correlate to each other, that's another topic. But this kind of like end-to-end systems, we will see more of these, whether we like it or not. But again, always when I put a slide on LLM, I put some limitations here. So you'll see a lot of limitations throughout my presentation. So here, for example, the real-time processing is an issue. Generalization, rare events is a huge issue with LLMs if they have not seen it before. They are very good at interpolation, not good at extrapolation. And then error accumulation over time. So from here onwards, whatever I'll talk about, it's mainly how to improve large language models in few domains, few areas. But that's equally applicable to robotics and non-robotic applications. Okay. But just to prove that I am a robotist by heart, so as Dr. Pravesh said that if you're a robotist, you must do experiments on your kids. So I did a lot of experiments with my kid. So here I knew my son liked the magnet, okay, refrigerator magnet, and I slowly moved it up. It was here before, and then I moved it up. And I was watching, of course, secretly. And he solved that problem. He opened the drawer. He stood there. He reached the magnet. His car is waiting. So, and he escaped the crime scene very, very quickly. So So this is just to prove that I'm a robotist by heart. And then Dr. Stacy was yesterday talking about it's amazing like how we can figure out these complex things. I don't know. How do we do that? So in large language models, what are the evolving trends? Where the world is going? Okay. So the craze started before ChatGPT, but ChatGPT really ignited it. So it was like one model will solve everything. Okay, we'll have one model, and that's it. All researchers can go home, relax. But recently, the trend is that we found that it's very inefficient to do everything. Okay, so there is this like we now have smaller. We are going towards smaller models, purpose-built models, mixture of expert models, so that we can justify the compute power that they're taking, and it become profitable to do that kind of applications. Then, of course, context alignment, then RLHF, reinforcement learning, agentic behavior, focus on real-time application. I will basically talk about more about agentic behavior, a little bit about model scaling and efficiency, how we improve that. So what are agents? Agents is, I think, very vague term. It's from different in different decades. It keep on changing its meaning. Okay. When I joined IBM, or after the DQN paper, the Atari games, the agents were. If you talk about agent, it has to be a neural network with reinforcement. But now, agent term is mostly used for large language models that can critique themselves. Okay, so I told you, large language model, when they start generating the output, they don't know the final solution. They just are generating the next most probable token. So you have to generate the full output before LLM can critique on it. Okay, so that's what agents are doing. This is a simple architecture for an agent, but there are more fancier ones you can play around with. So the simple few things that we have are LLMs remain black box. We know that. So we ask LLM to generate an output. We can use external tools if we want. Okay. And then the LLM, same LLM or another LLM, critique on its decision, and we keep on looping unless we are happy with the solution, given some criteria. In some cases, this criteria is very easy. For example, in case of software engineering agents, the stop criteria is when the unit tests pass. Okay, if all the unit tests are passing, we are successful. Okay. In other cases, it's very subjective. So, but anyways, this kind of architecture is catching up, and especially in software engineering domain, maybe that will be the first domain that this will create more business use case. Okay. During this time, this loop, they don't only generate the final decision or the final output, they also generate reasoning steps that they took to reach that decision. And I'll talk about that. Reasoning tend to improve the performance of these large language models. And it's also becoming a norm to hide those intermediate steps. Okay, so you ask a model to do something, then it does a lot of things, it takes a long time, and then it gives you the final answer. It hides everything that it did in the middle. And there are two reasons for that. First is it's very messy. All that outputs it generate intermediary, it's very messy. Secondly, if you get all those intermediate output, you can use to train your own model. And companies don't want that. Okay, they want to keep their model safe. They don't want you to distill their model. So an agent needs to be good at reasoning, planning, and tool use. Okay, how they can use external tools. So I'll be focusing on reasoning and tool use. So LLMs remain black box models. We have very few ways of improving large language models. The most common one that is still working is improving the data. Okay, so improving the input data. And how we do that, we gather very diverse data from many sources. We can transform existing data sets. Synthetic data generation has really transformed this whole thing. So you can distill bigger models, or you can generate data in some more fancier way. Extreme filtering of the data. So we have a lot of data that is noisy. How can you filter it with LLM, without LLMs? Here. Hyperparameter tuning. For example, I have now 50 data sets. In what combination should I have those when I train my model? Okay, so we have some very interesting research going on there. Of course, other parameters like learning rates still play a big role. And beyond this, there are other ways, like for example, human in the loop. Then we have reward models and the alignment part of it. I'll not cover that. So this is another area I'm working in, but I'll not cover that. I'll mostly focus on the first one. See, robots here. So tool use. So we know that LLMs cannot do everything by themselves. It will be very naive to think that LLMs will replace calculators, LLMs will replace databases. It will never happen. So they have to use external. They're good at that. They're getting better every day. So when we ask for something, for example, please make a banana yogurt for me, it needs to convert it into some commands that are understandable by the robot. And same goes for other applications also. So how do we improve that? We generate more data. So that's what we are doing. We generate purpose-built data for these LLMs to learn better. How it works is that we give a prompt, LLM then finds the best function or API that it needs to call. And it's compared to natural language, like LLMs are very good at natural language conversation, but this kind of structured input and structured output, they struggle a bit with it. So it's good if you can give them some very high quality data to train on. So here, for example, get the current weather in a given location. We give all the functions that are available with their description, all the arguments that are available with their description, and we leave the rest to LLM. Okay. So first we, for example, is it likely LS needs an umbrella now? So it needs to convert it into find the name of the person, get the user location, and then recommend something based on that. So this is what we are doing. We are transforming some external data sets. We are synthetically generating the data, and then we are fine-tuning our models. And of course, fine-tuning seems very complex, but as I told you, like the world is going to a smaller models, and we have methods like QLoRa and like where we can train very few parameters. Okay. That's why one GPU is enough most of the time. One GPU is enough for even fine-tuning the models. Function calling, again, seems very simple task. It's quite complex. It has many different subtasks. For example, API detection, which function to call, which parameters to call, how to sequence the APIs, nesting of APIs, like one API call depends on another API call, next best action, personalized response. So in the end, we are interested in the personalized responses. So based on everything that was done, what is the final response? And we generated this data, which is available in open source right now. We call it API Blend. And there is another one called Nestful. And the good thing about this is that it's taken from existing data set that were human curated in most of the cases, and we made it usable by large language models. It's very diverse domain. It covers a lot of different domains given here. So these domains don't matter. Like basically the model is learning to generate the function calls given the list of functions that you gave in the prompt. You can use, it's not that it's only usable in these domains. You can literally use these models in any domain. And the model trained on it is also made open source. So this one, Granite is the series of models that are trained in-house by IBM, and this is a 20 billion function calling model, and this is available open source. This is one of the best function calling models in open domain. There are a few proprietary models that are better, but they are expensive to use. So all these tasks get trained, and we hope the final model will be much better. So that's how you prompt LLM, your helpful assistant with access to following function call, and you need to be nice with the model, right? So, and then use these function calls to give me the solution. So this is how it works. This is a very famous benchmark in this domain called Gorilla function calling benchmark by Berkeley. And so our model is doing the best in the open models. As I said, there are a few proprietary models that are better. But in this size, in 20 billion or 8 billion, there is no model that is doing better than this. So you can see some performance here where this one, IBM Granite 8 billion code instruct is doing the best. And if you look at the hallucination versus average function detection, so hallucination lower the better, average function detection higher the better. So our model lies somewhere around here. Okay, so this is function calling. So as I said, so the agents need to be good at function calling and reasoning. Okay, these two kind of complete the agentic workflow. So how do we improve LLMs on reasoning? So when I found that I'll be traveling to this event, I started learning a bit more about South Africa. And this was the first query I ran on Google. So what's the area of South Africa versus Pakistan? So I originally come from Pakistan, so I'll compare areas with Pakistan. And it generated this response, like, which is clearly wrong. So I was so Pakistan is larger than South Africa by land area, and then it gives the numbers that contradict its first sentence. Okay. I was like, so simple. It's so simple for humans. So that's why I say, like, it's very difficult to trust LLMs at this point. And this is one of the best model that is running behind the scenes for doing that. So this is wrong. So what is reasoning? So like normal, a lot of time when we use a large language model, we don't care about the intermediate step. We just want the final answer. But then reasoning can improve that final answer. So I'll show some example. So reasoning is a way of systematic thinking. So instead of giving just a final solution or decision, it gives you the intermediate steps. There is formal reasoning. This is a problem. Like many people who come from reasoning domain, they always say LLMs don't reason, they will never reason, because they're talking of formal reasoning. And yeah, that is very common. LLMs are not formal reasoners. But there are good story makers like humans. So natural language reasoning, which is very subjective, they do that very well. We can call it informal reasoning. So there is ambiguity here, there's subjectivity here, but still, nonetheless, it does provide some insight into what the model is doing. Whether it's an emergent property of LLM or not. So emergent property is a property that appear after a certain threshold. Usually people don't talk about it these days, but last year, emergent property was a big thing. In LLM domain, another problem is that if you cite a paper that is older than 6 months, basically it's not acceptable. So it has to be, or maybe 6 months is too much, maybe 3 months. So that's a problem. So we see this, like LLMs get better After a certain threshold, they suddenly become good at reasoning. Before that, they cannot really do. And it's not only about parameters, it has to do with how you train LLMs also. As I said, so we'll focus on this natural language and a little bit about thinking fast and slow. Like, why do we need reasoning? It has to do a lot with System 2, which comes from this Thinking Fast and Slow book by Daniel Kahneman. So we know that neural networks are very good at System 1, the perception part of it, recognizing objects, doing very simple operations. They're very good, and so are humans. Like, if I show you, for example, a circle, everyone here will immediately recognize. You don't need to think about it, right? But thinking slow is where this reasoning really helps. Thinking slow can be for a very complex problem where you need to intentionally put effort into. For example, if I say, let's plan a vacation, okay, then that's a System 2 task. Nothing come to your mind immediately. You have to have a lot of information. Who is going? What is the budget? What are preferences? Are there kids? Or a lot of stuff. You have to figure that out. But the good thing will be that System 2, rational thinking, after you come up with the solution, you'll be able to explain your solution. I suggested you this place because this is your preference, because this is your budget, because you like this kind of food. Okay. So that's System 2 thinking. So real life systems involve both System 1 and System 2. So there are tasks where we don't care how you come up with a solution. I just want the classification of the image. There are tasks where I really care about the reasoning steps here. So in real life problem, for example, which car should go first? You need to understand first, like the System 1 helps you all the perception tasks, and then you need to know the rules, which country I am driving in, which city I'm driving in, what are the rules here, and stop signs and everything, and then you can decide which car should go first. So usually we are doing both of them together in a very seamless way. So chain of thought reasoning, again, so this is the simplest form of reasoning that large language models do. Instead of asking the large language model to give you the final solution, you prompt it with the intermediate steps also. So instead of giving this example, so in LLM you can give few examples and then you can give the question. So, and it will try to answer in the same form that the examples you gave. So instead of giving this as an example, you can give this as an example where you give the intermediate steps. And when you ask a question to LLM, it will try to mimic that and it will produce the intermediate step. And the performance usually improves when you give chain of thought reasoning steps. The performance, if you see in the plot, the line with the bigger circles, that is with chain of thought prompting, the performance usually improves. Okay. So that's why we can say to some extent that reasoning is helping. It's not completely made up stories. It's doing something useful. So here, this is an example where without chain of thought, with chain of thought, what is the largest state bordering Mississippi River? And it comes up with Louisiana, okay? And that is wrong. When we ask, we just think step by step. That is a zero-shot chain of thought prompting method. Then it starts thinking about, first it lists the states that are bordering Mississippi River. Then it kind of finds their area. Then it chooses the state with the biggest area. In this case, Minnesota is the largest state bordering Mississippi River. So you see how going from simple prompting to chain of thought prompting can help in many cases. And of course, now we are talking about beyond chain of thought. Chain of thought is kind of history now. There are much better methods. For example, tree of thought is gaining some traction again. It's already in use, but recently, because O1 preview hides the reasoning steps, So this allows you to do a lot of compute in the backend, and tree of thought can be one of those methods. But there are others that is not the topic of this presentation. So the $1,000,000 question: are LLMs able to reason? So they do perform well on reasoning benchmarks. Okay, whether those benchmarks can represent real reasoning or not, that's another issue. And we have some, for example, serious problems with the current benchmarks. First of all, they focus on particular domains only. Then they are very templated, like they were generated pre-LLM era. If you follow that template, you can crack it without a LLM also. Okay. And there is a contamination issue. Like you never know if the large language model saw those benchmarks during pre-training, because during pre-training they kind of use the whole internet to train themselves, right? And they may exploit these artifacts and templates, and they might find shortcuts. But the good thing is that recently there is research on the benchmark that are generated on the fly. So you can be sure that the LLM didn't see that. But out of distribution issue still remains a problem. So here I put some like numbers from the latest model, one of the latest model 5.3, which is doing very good on benchmark. So for example, Big Bench Hard is a benchmark that we really care about in my team. Similarly, MMLU, it's at the top. And if you look at like GPT 3.5 numbers and the 5.3 models in the second column and third column, they are very small compared to GPT 3.5, which is in hundreds of billions of parameters. And these models are like 8 billion parameters. So being much smaller, they're performing better than GPT-3 kind of, which is amazing. Like, so LLMs do well on reasoning benchmarks, and sometimes better than human, non-expert humans. Okay. What we are doing about improving LLMs on reasoning tasks, we are using knowledge graphs to create data sets to train these large language models. So we believe that LLMs were trained on a lot of unstructured text, but a lot of knowledge is encoded in these knowledge graphs. Okay, and it was generated. Many of them were generated manually, painfully over decades, and that can be used to train these large language models. Knowledge graph cannot be used directly in pre-training, and the reason is that LLMs don't like this very templated text. If you give knowledge triples to LLMs, they will start forgetting other things. Okay, so these templated data can be very toxic to LLMs. So we work with these knowledge graphs, how to prune these knowledge graphs, how to clean, how to find the relations that are relevant for natural language conversations, and then we generate data sets out of it. So this is, for example, a paper concept, which this is a CSQA, common sense question answer. I believe this was one of the first papers that did something like this, used knowledge graph to create trainable data, but they also use a lot of human annotation here. So we are trying to do that with LLM-based annotation or some other methods. So for there are like, in addition to what I said, the knowledge graphs, there are other methods that do a lot of compute during the inference time. And for example, tree of thought, or I will show a few examples, chain of code. They do a lot of compute at the inference time, and they usually perform much better than simply prompting these models. But that is very expensive. If at inference time you take a lot of tokens to reach the output, it costs a lot. So we want that inference time to be very quick, and we want to move all of that compute to the training. Okay. So So what we do is that we use these algorithms that are very good at inference time. We generate very good data, and we want our inference to be very speedy and cheap. So, for example, this is a question: which one is heavier, 1 kg of cotton or 1 kg of steel? So for humans, it's a no-brainer kind of. Maybe for 4-year-old kid, it's nothing. But this question took GPT-o1 preview 22 seconds to reply. And right now it's running in the demo mode, so I don't know how many tokens it really used. I didn't try it with API call, so it might use like thousands of tokens before it reached this conclusion. Okay, it did reply it correctly. So these 22 seconds for such a simple reasoning question, it's such a waste of resources. So what we do is that we do these very complex inference for generating high quality data, and then we feed it back and we train the model to make it better in the first place. So we can save all this compute at the inference time. A few papers, Self-Discover is a very interesting paper that you can look at, where they provide many different kinds of reasoning and ask LLM to pick the most suitable kind of reasoning and apply it. Chain of Code, where they claim that, and actually we verified this claim, in many cases, these language models are better at generating code than they are in generating language, because they have seen very high quality code data and very unstructured kind of text data, or very noisy text data. These are few papers that you can look more into. I really want to share more details on what I'm doing, but it remains confidential at this point. We hope to publish it soon. So if you are connected with me, I'll share some links, and then you'll find out very quickly more details about what we're. Another project that I want to really talk about is IBM's approach to open large language models versus some other open source models that are available. And these two projects, Instruct Lab and DGT, which is data generation transformation pipeline, is what I will briefly talk about. So open source, so IBM and Meta co-launched this AI Alliance, which is all about open sourcing these technologies. Open source large language models are very common. Many people are using that, but they have few very serious challenges. Like, we can call them open parameter models, but they are not really open. We don't know how they were trained. And that's what IBM is trying to change. So in IBM's open source model, the project Instruct Lab is trying to give other people ability to contribute to the training of the model. Okay. How we are doing that is, so in Instruct Lab, there are a lot of skills or that can be added to the models. We have a taxonomy that is available, but someone can come in and someone can say, okay, I want to do chemistry reasoning, and the IBM's LLMs are very bad at chemistry reasoning. So what they can do is they can add a new skill, they can add a new knowledge, and at the back end, when the next LLM will be trained by IBM, we'll generate a lot of data in that domain using the examples that were provided, and we'll put it into the training of the model. So in a way, the community can contribute in the training of the model. So this is the taxonomy, like the skills that we have. Like it's a very big taxonomy of skills and knowledge, question answer, math, compositional skills, and then other kind of thing. The difference is because we are giving the taxonomy. So if you remember the self-instruct paper that came before ChatGPT, it generates a lot of data synthetically and train the model on that synthetic data. But there is really no control over what kind of synthetic data is being generated. But by giving this taxonomy and giving examples in various different domains, we are kind of making that very broad. Like we are giving examples in very broad areas. And when the model generates these synthetic data, We hope that it will be more diverse. It will not be following the distribution of the parent model, the teacher model. It will be more diverse because of these diverse examples. Results, so we saw like on different models like llama models, mistral models, that we can improve significantly on many benchmarks using the instruct lab method. So this is my, I believe, second last slide. So DGT is another way of making contribution to IBM models. So in Instruct Lab, all you can give is few examples of the tasks that you're interested in. In DGT, you can actually contribute the whole pipelines. Okay. So if there is a better way of generating synthetic data, for example, we have pipelines for generating API data, for generating natural language to SQL data, which use verification and stuff like that. So if you have some ideas and you want to generate pipeline, then you want IBM models to get better and then use those models, this is a way to do that. This is also open source now. I should have put the link. If you search with DGT IBM, you will find this. So final conclusion. So foundation models, LLMs, in one way or the other, will have major impact on how we do robotics. Okay. LLMs again remain part of the solution. They are not the final solution. So I am not very much I don't believe in these end-to-end models that put LLM and forget about everything. I don't think that will work because there are major limitations in their capabilities. The most important one being are they safe? Is it safe to just do that? I also discussed agentic behavior, how we can improve that a little bit. Okay. And at the end, IBM's approach to open models, and I welcome you to look more into that. And you can also contribute directly to IBM models. And as a feedback, you can use those models in your research. And as I said, so some of the information I was not able to share because it remains confidential as of now. So please connect with me, and you'll see we'll open these papers very soon. I'll share that on X and LinkedIn also when we publish those. Thank you. Any questions?
Questions from the floor?
So you spoke about fine-tuning large language models to make them more intermittent. But there's been quite a lot of research in doing that rather using retrieval augmented generation techniques with knowledge bases. And I was just wondering what your thoughts are with your work on the two methods.
So RAG remains a very important area. There is no doubt about that. Okay, but again, how do you make your model better at RAG? And secondly, RAG does not include these intermediate reasoning steps. So even if you retrieve something from some document or some knowledge source, how are you coming up with the solution? You still need those reasoning steps for interpretability reason, for explainability, for the trust reason. So RAG remains complementary to everything that I said here. There is almost no overlap. Yeah.
You mentioned using the large language model and then teaching it to kind of parse instructions in order for you to have tool use. So, for example, on a robot, how, if we can't really trust it, how do we then, what's the kind of the gap between being able to actually use it on a real robot?
So the thing here is with function calling, one of the best thing is that we know what functions are available. Okay. And when we prompt LLM, we only give those functions. We tell it to choose one of these 5 functions. And whatever it chooses, we can always check the output and we can see if it was not one of these 5 functions, then discard it. Okay. So that is one thing. And secondly, all the safety issues, still, even within those 5 functions, one of them can be very unsafe given the situation. So that remains an open issue. So how do we deal with safe execution of that? It's an open issue. Unfortunately, LLMs don't help a lot.
Yeah, one question from me. One of the things that we're seeing currently is that, like, especially in foundation models, is evaluation is really difficult to do, especially if you have like very bespoke applications of robotics. So how do we kind of move it from like this kind of low-level reasoning where you have a set of tasks that the robot is supposed to do to this kind of general-purpose robotics world where foundational models are supposed to be proving their worth? How do you think we can kind of bridge that gap, knowing that there are some challenges with evaluation?
That's a topic we are struggling. So it's a very good question. But the way we are doing it, so evaluation, the best evaluation we can do right now is human evaluation. Okay. And just before I was coming here, I saw a paper where they say that LLMs learn to deceive human evaluators also. Okay. With reinforcement learning, with human feedback, they actually learn to deceive human evaluators, get highest reward from them. Okay, so this is the problem. So I would say the best thing we can do right now is to come up with better evaluation benchmarks. Most of the benchmarks, like I showed you, Big Bench Hard, MMLU, in reasoning domain for API domains, they were pre-LLM era. And although you should not never look at the benchmark examples, but I did. Um, so for some subtasks, I wanted to understand it. They are very trivial compared to the capability of LLM. They're very template based. So our LLM was not working at all on one benchmark. And I saw in the evaluation, they're looking for full stop at the end of the sentence. And our LLM was doing everything perfect. It was not generating that full stop. And we were getting zero reward for that. Okay. So that kind of things happen. And it's unfortunate, but we again have to rely on better LLMs to evaluate our LLM's output. So it's again open question. But coming up with evaluation benchmark for the problem that you're working on can be a huge contribution to research community.
Any other questions? Thank you very much, Jesse. Very enlightening. Next, we have Cameron Otto from the unit, who will take us a little bit back to legged robotics and legged robotics fully. Yeah, thank you, Cameron.
So good morning, everybody. My name is Cameron Norton. My master's project that I'm going to be presenting to you on the progress I've been making is titled Cheetah Head Stabilization and Tracking Using Computer Vision and Inverse Optimal Control. It's quite a mouthful, but I'm being supervised by Dr. Stacey Shield, who presented yesterday, and Associate Professor Amir Patel. I'm also part of the African Robotics Unit, which is also colloquially labeled the Cheetah Lab. So a lot of our work that we do in the lab is inspired by, as you saw yesterday, Dr. Stacey Shield presented, is inspired by cheetahs. So we do a lot of bio-inspired robotics. So the objectives of my project include quantitatively understanding how cheetahs use their neuromechanical control. So how does the signal from their brain quantify what's happening in their environment, and how does that get to its muscles to stabilize its head? And exactly what does that mean in a control sense? Then I want to derive that implicit cost function that it's using when it stabilizes its head. And I want to understand that exact control mechanism that it uses, so that hopefully we can apply it to leg robotics, and as well as, we can apply it to leg robotics and also contribute to conservation efforts. So the more we understand animals, the better equipped we are to help them. And that is the idea behind it. But also, if you have a robot, especially a legged robot, that's moving a lot, it's running, it's doing a lot of agile tasks, we want to be able to stabilize a sensor suite on it. We want to be able to stabilize a limb. We want to be able to stabilize something that's happening independently of its motion. Another way I like to think about it is if you've ever seen a video of a chicken and the person holding the chicken is moving the chicken around and its head stays stable, almost as if it's on a gimbal. Something similar happens with cheetahs when they run and do agile motions. And the reason we use cheetahs, as Dr. Shield explained yesterday, was because they are super highly adapted to perform these agile tasks at high speeds or independently of one another, very high speed tasks or very agile tasks. So my project, what we do is we put cheetahs in a bucky, which is like a pickup truck for those who aren't familiar with buckies, and we drive them around on dirt roads. This is all with ethics approval, obviously, and this is done at a conservation site called the Anfendijk. So it's with cheetah handlers and everything. But we put the cheetahs in the bucky and we drive them around and we observe what happens with their head and when they flick their tail to stabilize themselves. I'm more focused on the head. We've got another student focusing on the tail. But it's really interesting to see what sort of compensation it makes for the ground perturbation underneath it that we provide with the bucky. So to do that, I need to do markerless motion capture, which is really, really hard on a moving animal that doesn't have, it has its spots, but those are hardly feature points if you are analyzing lots of different cheetahs because they all have different spots. So it's really hard to get markerless motion capture on something that's moving, but it's also a natural object. It can compress and expand, and it's a living being. It's really difficult, and especially to get these data points in 3 dimensions, because in order to analyze what's happening from a stabilization perspective, I need to know what's happening in 3 dimensions. I need to know how the ground plane is moving, how the cheetah moves relative to the ground plane, and it's quite useless if you're just doing that in 2 dimensions because the cheetah is a 3-dimensional. So to do that, I needed to use some computer vision, and what proved the most difficult of this was the camera calibration. I need to work in MATLAB because my project is sponsored by MathWorks. And so MathWorks at the time that I did this project didn't have the capabilities to do multi-camera calibration for a 3D reconstruction. It has multi-camera calibration when the camera is moving around an object, but it does not have yet the functionality to do multi-camera calibration to reconstruct something that is stable and standing still. So I actually managed to do that, and my project will be published as a MathWorks example, which is really exciting. So the challenges included, do we use fisheye intrinsics, normal intrinsics? We decided on fisheye. Then we need to sort of find a way to relate those stereo pairs to one another because we calibrated, basically we used one camera as a reference, which is the blue camera over there. And then we stereo calibrated camera 1 with 2, and the other camera 1 with the other one. And that's how we related them all to one Another issue was that the data I was using at the time had sparse calibration data because we didn't know we'd be using it for this purpose. And also we tried to use sparse bundle adjustment for the extrinsics, which is a way of refining the results of it. But also at the time, MATLAB did not have the capability to define that those calibration boards were planar. So they were adjusting the points on the calibration boards to be anywhere in that 3D zone, whereas you need to know that the calibration board is a plane. And so we've also suggested that to them. So the way that I validated my calibration was to use epipolar lines. So the way these work is like every colored line is a line through an estimated plane. And then in the other image, the line of the same color is a line through the estimated plane in another view of a stereo camera. So to also see this is Dr. Shield in the buggy with the calibration board. You put a point on her right eye, and you can see the epipolar lines in all the other views going through her eyes as well, which means that it was accurate. We've also subsequently had it verified by the computer vision team at Artworks. And yeah, now we were ready for the 3D reconstruction. So then I went and I labeled and I labeled and I labeled and labeled and labeled and labeled. Like thousands of photos of the frames of videos of cheetahs that were collected. And I did this in MATLAB, but because it's thousands and thousands, I discovered a need for automation, especially since we've collected new data. So this is the 3D reconstruction here that I managed to do. These are the 3 views of the cheetah and the reconstruction that I produced from the labeling, the calibration, and then my own sort of triangulation method of reconstruction. But as you can see, it's not good enough. Like this is 60 frames per second. It's quite sparse. Not all of the points are represented properly. And it's not really possible to get an accurate reconstruction of the head stabilization from this data. So this necessitated a field trip. So I went with a colleague, Damien, to go and collect new data. And the way we did this was we used 4 cameras this time. We mounted them on a clamping bar in the back of the bucky so that we could stabilize the cameras on the bucky because there was a bit of shake in them. We also used a much bigger bucky because the cheetah was self-occluding. So if I turn around like this, you can't see my arm. But if I had another camera there, you would be able to see my arm. So that was the idea, is like instead of 3 cameras, we used 4. The cameras were also newer. We had high frame rates, high resolutions. Yeah, we also collected a lot more calibration data, which would serve me in the future. And this is an example of some data collected. You can see this is Amelia, the cheetah. You can see as the car is moving around, she's flicking her tail, she's keeping her head still. And I think my sort of idea of why the cheetah keeps its head still is because it needs to see stuff. If it's running really fast and it's got its eyes tracking prey, it needs to keep its head still because like if you're trying to look at something and your head's shaking the whole time, it becomes quite difficult. So that's sort of my hypothesis behind it, but the whole point is I need to prove that. And yeah, so when I mentioned earlier that there's a need for automation in the labeling, I've started looking into something called Deep Lab Cut, which is widely used by my colleagues as well. It's a open source 3D pose, well, it can do 3D, but it's a pose estimation tool. You train a convolutional neural network. You can choose the architecture. It's quite cool in that sense because you basically just build up on a pre-trained network. And Xenoset, a paper by Dr. and Professor Patel, which also included other people as well, built on Deep Lab Cut as well. So as you can see, there is some room for improvement. The shoulders sort of label over each other. The labels are quite jittery. But once I improve the labeling accuracy, speaking to another colleague, the jitteriness can be fixed with outlier detection and filtering and all sorts of things. So it's not a problem per se, but I would really prefer it to be accurate because that was the whole point of collecting new data. Yeah, this is sort of where I'm at now with the labeling. I want to be able to label accurately before I go into processing the new data in a reconstructed way. But once I've got my reconstructions and the 3D data, I can get going on analyzing the inverse optimal control part, which, yeah. After I've calibrated and done all of that reconstruction priming, then I can go and reconstruct, do the quantitative analysis on the 3D points, and hopefully infer some sort of neuromechanical control algorithm that the cheetah uses and apply it to robotics and also conservation. So thank you very much. Are there any questions, concerns, comments? Thank you.
Very interesting work. So, what do you pick, put on the bucky to get the motion? Like, do you put some sensors there? Or
Yes, we did. So in the first collection that Dr. Shield and another colleague, Gavin Foster, did, Gavin actually made an IMU. If for anyone who doesn't know the acronym, it's an inertial motion unit. It like captures accelerometer data, GPS data, all sorts of things. And we actually mounted that on the bucky, so it's moving at the same time as the bucky. But it actually broke when we did the second one. We had like an hour of it working, and then we don't know why it broke. I spent hours soldering, hours trying to fix it. But the long and short of it was we actually ended up isolating the IMU sensors on my phone and securely taping my phone to the top of the bucky. And we do have IMU data, so I will be able to do some sort of relational reconstruction between how the bucky moves versus how the cheetah moves, and be able to quantify that as well.
it's not like calibrated with the frame, like exactly when you take the frame.
Yes, everything is time synced. I also created code to automate that. So I would go and manually watch the videos and say, at this time point, the cheetah flicks its tail, and then my code goes and does all of the time syncing and cropping of the videos, because the videos are like 13 minutes long at 240 frames per second. So you can imagine that creates thousands and thousands and thousands of frames. But we do time sync it all, and I time synced using audio syncing, because I could sit in the middle of the bucky and that reduces the like millisecond inaccuracy in obviously speed of sound.
So just to add there, as much as it's kind of helpful for us, or potentially useful for us to have that reading of the car's movement, at the moment our working hypothesis is that the motion of the car actually doesn't really matter all that much, because what we saw from the first set of data that we collected, where we had these timestamp locations where it's like, okay, here's a tail flick, here's where the cheetah sort of stumbles. There were no features in the car movement that actually predicted that, because I think in our heads initially, when we had the idea of, oh, okay, the cheetah's in the bucky, we thought it would be like this much more like isolated. We were just imagining the cheetah like politely standing in the car and moving with the car, and then flicking its tail in response to like if it goes over a bump. But actually, as you saw there, the cheetah's like pacing. And more often what actually happens is that the cheetah seems to kind of like trip over its own feet or sort of lose its footing independently of what the car's doing. So it's almost more like a sort of second order relationship, where what you're actually looking at is still the relationship between the head and the body, or the tail and the body. And then it just so happens that there's underlying that the car is acting on the body as well.
So we can't assume that the perturbation is coming from the bucky. We can model it as if the perturbation is coming from the body of the cheetah, and that the neck is the stabilization mechanism, but we don't know yet. So it is useful to have the IMU data. Any other questions?
Just one quick question. So I saw like some of those points were disappearing in the stuff. Is it maybe kind of like worth kind of having them like have all of the points always in the image, and maybe kind of like use a measure, for example, the point at the next time step should be at least epsilon close to that same point.
Yes. So we can use interpolation as well as like filtering methods, but I would prefer just to at this time just continue training the neural network, see how accurate I can get it, and give myself like a time cutoff before I start the filtering and interpolation.
I'm curious to know how you achieve very accurate time syncing between the two cameras. Because if I heard you correctly, you're saying that the frame rate is about 860 or
240 frames per second.
240. what sort of error tolerance do you have for the time sinking?
So at the moment, I want to say a zero frame accuracy, a zero frame error, because I also, as well as using audio syncing, I also use light syncing, because speed of light as well is very fast, sub-millisecond accuracy. So I took a flashlight and sat in the back of the bucky and turned the flashlight on and off. And then when I go through one video, I just scrub to that part of the video in all of the different cameras at the same time, and I can see at what point does that light switch on in all of the different cameras, and that way I get sort of a zero frame accuracy, but I don't want to assume that it's zero frame because there is some slight error with the speed of light, because like speed of light is quantized, like Great, thank you so much.
Thank you, Cameron. And then next from the Electronic Systems Lab, Jean van der Walt.
Yeah, so good morning, everyone. So my name is Jean van der Walt, and I'll be presenting my research that forms part of my master's project, which is titled Qubit, Walking for Bipedal Robot. My supervisor was Dr. Callan Fisher, and we from the Electronic Systems Laboratory at Stellenbosch University. Before I start with my presentation, just a quick overview of it. So I'll start with some background information on legged robots, especially bipedal robots. I'll then discuss just present the robot I did my testing on, which was named Qubit. Next, I'll discuss the trajectory generating technique we used to generate the reference walking trajectories for Qubit, which was using trajectory. I'll then discuss the control architecture we used to implement the reference trajectories in real time on the platform, and then talk about the experimental setup and the results obtained from the walking experiment, and then finally just a quick conclusion. Okay, so over the past decade, legged robots have made tremendous advancements to the point where agile locomotion on unknown rough terrain has been achieved. Despite these advances, walking is still considered a very complex challenge for legged robots. The robots that are capable of this feat are typically very expensive, or they are developed in industry with very little technical information available due to intellectual property restrictions. The cost and duration of developing these platforms are the costs are very expensive and the duration takes very long. So it makes it quite infeasible for underfunded research institutes to develop these platforms. Despite all these challenges, the interest in the literature for bipedal robots has still grown, and a lot of focus has been put on energy efficiency and robustness as well. And the other feat that also contributes to the increase in interest is that bipedal robots are also capable of moving through very rough terrain, and that they can also work very well in environments that are tailored for humans. So the ideology behind legged robots has predominantly been inspired by nature. For example, the ostrich, so they have extremely good maneuverability, mobility, and agility characteristics across very diverse terrains. But still, achieving these bio-inspired characteristics is still considered a very difficult challenge. Because of their complex and nonlinear system dynamics, it is very difficult to get that match between an actual animal and available research on animal maneuverability is also very limited. So researchers don't know why certain animals do certain things. So that's why there's also a lot of research on that. And that obviously contributes to translating biological insights into locomotion techniques for legged robots. So just another story. So AI researcher Hans Moravec, he famously stated that it's very easy to train robots to perform tasks beyond human abilities than to actually train them to do everyday human actions. And this is a very fundamental thing, highlighting a big difference between humans and robots. So humans seamlessly integrate perception, so what we see and feel with motor skills, what we do, where robots rely on sensors and algorithms to convert their perception into action. For example, just take walking, for example. So the intricacies associated with walking, such as adjusting balance, coordinating leg movement, adapting to terrain, and overcoming obstacles, we can all do that, as humans can do that automatically, but robots, they have to do this in real time using sensors and algorithms, which is very challenging. Next, I'll just give a brief introduction to my robot. So Hubert is a 60-year freedom bipedal robot, which is specifically designed as a low-cost platform. There's locomotion techniques on. So the robot has 4 active joints. So it has 2 hip joints and 2 knee joints, which were realized using cube mass motors. And each motor had a encoder and speed controller for feedback purposes as well. So the motors are all located at the hips, actually located there, and the knee torques are transmitted via belts that were located inside the femurs of the robot. The ankle joints were fixed, which resulted in the robot having 0.4 feet as well. The total weight of the robot was 8.91 kilograms, and each leg was 0.54 meters long, roughly. So the robot was designed without abduction and adduction capabilities. It can't move its legs sideways, so the motion was only restricted within the sagittal plane, so that the robot can only move forwards and backwards, not sideways at all. And due to this limitation, we had to attach the robot to a testing setup, so that just helped keeping the robot in the upright position, because if it starts falling over, it cannot move its legs sideways to actually keep its own balance. So the testing setup consisted of a pivoting arm, which was on a bearing block that ran on a linear rail. And when the robot then moves forward or backwards, the testing setup just followed it forward and backward without disrupting the dynamics of the robot too much. So we used MPC as the main control architecture for this project, and therefore we needed a reference set point trajectory. So we used trajectory optimization techniques to generate these reference trajectories offline. For those of you who don't know, so trajectory optimization is a process of designing a reference trajectory that minimizes some measure of performance, which in this case is a specific cost function, while satisfying a lot of constraints about the robot. So then the MPC controller can take this reference walking trajectory and then implement it in real time on the platform. So first we had to develop a mathematical model of the robot, and we used Euler-Lagrange dynamics in the form of the manipulator equation, that's the manipulator equation over there, to model the robot. So the robot, to make sure that it's a very computationally feasible model, we modeled the robot as a system of interconnected rigid links. So each leg had 2 rigid links, the femur and tibia, which was connected by a rotary joint, which is the knee joint. So the torques were applied to both the hip joint and the knee joint. And then there was the generalized coordinates and the applied torques and the ground reaction forces associated with our mathematical model. So onto the optimization method. So the trajectory of each state variable was discretized into n node points using 3rd order polynomials. And then the trajectory between node points was represented using a Runge-Kutta basis with 3 collocation points. So you can see that the black points are the node points, and then in between the node points, we had 3 collocation points as well. So 3-point radar was used to integrate the equations of motion from node I to node I plus 1 using those 2 equations. And then also we had to ensure that there's a continuous trajectory. So what we did was we implemented those 2 constraints to ensure that the 3rd collocation point of node I aligned with the same node point as node I, basically. So due to our robot making a lot of ground contacts while walking, it had to be constrained to only make or break ground contact at node points. So that means that the ground contact remained in effect during the collocation intervals between the node points. So that implemented a variable time step. So that increased the resolution of node points at critical points in the trajectory, for example, at ground contact points, and then also lower the resolution of node points at less critical points, for example, for aerial phases. So we had to, that constraint was used to then define the time that was allowed for each node point. So it was either 0.05 or 0.15. And then also the node times were split up amongst the collocation times in between the nodes. And also, once again, to ensure continuous trajectory, we had to align the end time of node I plus 1, node I at the third collocation point with the end time of node I plus 1. So we did not, so the ground contact order was not predefined, so the optimizer had the freedom to select the optimal footfall pattern and contact type during the optimization process. And we used through contact optimization methods to achieve this. So through contact methods contain numerous complementarity constraints, which are very difficult to solve. And therefore we had to redefine, so just first what the through contact methods are. So through contact methods ensure that the ground reaction forces only act on the feet when the feet are in contact with the ground. And due to their complexity, we had to redefine the complementarity constraints associated with these methods using epsilon relaxation techniques. So during the optimization process, initially epsilon is set equal to 1,000, and then after each successful solve, we will lower epsilon with a factor of 10 until we achieved a solving accuracy of 10 to the negative 5. So for the generated trajectory, the robot started and ended at rest in a crouch position with the femurs and tibias at 45 degrees. We also added a bunch of other constraints like general bound constraints, a linear motor model. We also added knee angle constraints, step pattern constraints, foot lifting height and body height restrictions, as well as average velocity constraints over the entire trajectory. And we also implemented the minimum time cost function because this sort of created the smoothest trajectory. And so this was the generated trajectory that we deemed most optimal for the physical platform. So that was then the trajectory we implemented. So this is the control. Over here just gives a brief overview of the control architecture we implemented. So the optimal reference torques was calculated using a discrete time MPC finite horizon MPC controller. So MPC is a control scheme that uses a model of a system that predicts the future behavior of the system over a finite time horizon. We also use receding horizon control, which means that the complete future control trajectory is described, but we only implement the first sample of the control signal and then neglect the rest. And then at the next iteration, we recalculate the optimal control trajectory and then implement the first one once again. So the MPC controller receives the reference trajectory as its reference and then generates the optimal reference torques at a frequency of 100 Hertz. This then goes through the joint level controller, which fine-tunes the reference torques from the MPC controller and produces the motor command at a frequency of 2 Hertz. So the joint level controller only receives position feedback from qubit, and the MPC controller receives position and velocity feedback. So once again, we needed a model of the robot to generate our MPC controller. So so we also once again modeled it as a system of interconnected rigid links and then used Euler-Lagrange dynamics in the form of a manipulator equation to model this. There was 2 slight differences between this model and the trajectory optimization model. It was just the way we defined the point angles that made debugging during the walking experiments easier, and we also excluded the x-coordinate of the body, robot body, because we didn't have an accurate way to measure the x position and velocity of the body during the walking experiment. So the MPC controller required that the model of the robot should be in state space form. So we had to convert the manipulator equation into a state space equation by defining the state vector and input vector like that. So then we can redefine the manipulator equation as follows, but it was still not in state space form due to this constant gravitational potential term there. We then use this nice trick. We add the gravitational acceleration to the original state space vector, and then you can redefine it as a continuous state space model. This was then discretized using the sampling frequency of the MPC controller and then converted to an augmented state space model by redefining the state vector as follows. So then this was the model we used for the MPC controller. The MPC controller calculated the predicted output of the system using that equation, where the F and phi matrices were calculated using the A, B, and C matrices of the augmented state space model. The cost function of the MPC controller was defined as follows, with the first term minimizing the error between the predicted outputs and the reference trajectory, while the second term reflects the consideration given to the size of the change in input signal when we try to minimize the cost function. To calculate the optimal reference torques, which were then sent to the joint level controller, You set the derivative of the cost function equal to 0, and then you can calculate the optimal reference torque. So the joint level controller is often used in conjunction with MPC controllers, but they are not very well documented in literature. So we use this to increase the stability of the walking gait by increasing the trajectory tracking, decreasing the trajectory tracking error, and also increasing the real-time responsiveness of the controller. So the joint level controller was defined as a proportional controller with a feed-forward reference term. So we took the reference torques and then added an offset to it by calculating the difference between the reference angle and the actual measured angle, and then the multiplying it with a constant gain. So it got the reference torques at a frequency of 100 Hz, generated the motor commands at a frequency of kilohertz. So that means that it performed 10 iterations before receiving new reference torques from the MPC controller. So this is just an example of one of the walking experiments. So the robot starts off with its legs straight in the upright position where it calibrated the motors and zeroed the encoders and everything. Then crouches down into the starting position with the tibia and femur angles at angles of 45 degrees. So for this walking experiment, it was specified that the robot should take 10 steps forward, 5 steps per leg, and then also it then stops again at the same position as the starting position, again at 45 degrees. So you'll see that we struggled a little bit with the foot lifting because modeling the ground context was really difficult. So it was a lot of back and forth between this trajectory optimization and then testing it again and so on. But this was ultimately the best we could do because of the modeling inaccuracies between the trajectory optimization model. So on to the results. So this is just comparing the reference trajectory with the actual measured trajectory. So the blue is the actual ones and the orange is the references. So it actually performed quite well. The left femur trajectory tracking error was about 8.5% and the right femur one was around 10.8%. Looking at the left and right tibias, it was also actually performed better than the femurs, and they were quite similar. The one was about 7.75% and the other 7.85%. But importantly, what we wanted to see was to see how much the joint level controller actually contributes to the walking, because otherwise, what is the purpose of the MPC controller then? So what you can see here is that the blue shows the MPC controller torques and the orange shows the torque of the that was calculated by the joint level controller. So you can actually see that the reference torques from the MPC controller still contribute to the main magnitudes of the torques that are sent to the robot. So it just shows that the joint level controller was only used to add that little bit offset. So when the leg does not move, it just adds a little bit so that it starts moving and then it performs. So there's a little bit difference between the two, but it's minimal. And the same can be seen actually for the left and right knee motor torques as well. So in conclusion, so the results confirm that the reference walking trajectory can actually be accurately tracked by the proposed controller. Although the robot did not lift its feet properly, it was still able to track the reference trajectory quite well. So that resulted in Qbert walking a distance of 0.8 meters forward and taking 10 steps in the process. We also achieved an average trajectory tracking error of about 8.65% over the 4 joint trajectories. And despite all the inherent modeling challenges, still just demonstrated remarkable accuracy. And this is obviously attributed to the additional joint level controller, which just made sure that it always got that extra little bit. So as the walking gait is obviously periodic in nature, it can then also be extended to any desired amount of steps, and that increases the distance that Qbert can walk. Okay, thank you very much. Any questions? Yes.
Just 2 quick questions. The first is, does that pole that kind of keeps the robot like on that axis?
Yeah.
Does it like exert some force on the kind of like vertical axis? Like does it prevent the robot from falling if it wants to fall?
No, so it can, up and free to rotate up and down. So it will, if it falls, it is going to fall down, but it just stops it from falling sideways because the legs can't move that way. So it's only for stopping it from falling sideways, but you can still fall forward, still fall backwards, and still fall up and down as well, or jump up and do weird stuff. Yes.
Okay, I see. So that's the second question is. I don't know. So this is I'm not quite familiar with this field of learning dynamics from demonstrations, but like is it possible to kind of learn the dynamic of the robot from like doing doing random so like applying random uh, motor forces to the robot to kind of get some random trajectories and then trying to learn the dynamics of the robot from that? Is that like something that is like possible?
So you can definitely do it, and like if you use something like a Raybird controller where you need like the constants of the spring damper constants you use for that, then you do that. But the problem is like if you just put random stuff on this, it breaks quite easily, and the motors are really expensive. So it's not the most feasible way of doing it, but I'm pretty sure you can do it. But it's if you only have limited
like random with some constraints on the forces that you are putting.
So you can do it, I think, but I don't think it's a bit of a process.
It's a bit more complicated than that because it's not, you can't really just bound the forces universally. It's actually, you have to bound them in a way that still takes the model into account, because I mean, like with our robot as well, it's like if you just exert even a smallish force in the wrong direction when the leg's in the wrong position, it's going to snap its own leg.
I see.
So most of the time, even though RL is really popular for training legged robots, it tends to be more in like a sim to real kind of space where most of the training's done in simulation and then ported over.
Interesting. Okay, that is very useful.
What were some of the things that you guys did to try and address the friction problems that you guys had?
So the initial problem was when I first put the trajectories on the real robot, so it was dragging its feet on the ground, so it didn't lift its feet off the ground. The other problem, so I didn't build the robot; it was built by a previous master student. I just refurbished it a little bit. But so he tested it with force, pressure sensors in the feet, so that we can get some sort of idea if the feet are in contact with the ground or not. And then we could have also added that to the cost function, but it didn't actually, because the feet are molded from like silicone rubber, so it was quite difficult actually to get that if you place the pressure sensor in the feet to get accurate measurements from that. So we scrapped that idea then. But so we just went back to the trajectory optimization model, and then we focused on making the transition when it lifts its foot up off the ground to make it as like smooth as possible. So it's not just a big impact, so that it can lift its feet like over a longer horizon. And I also try to increase the time it takes to take a step, so that there's enough time to actually achieve the torques that it's needed to lift the leg off the ground as well. So that was a few things we tried. It was a bit of like a trial and error situation. We'll try a lot of things, see if it works and implement it, and then just move forward on that as well. Yeah. Okay, any more questions?
Thank you very much, John. We'll now proceed for a coffee break, and we'll be back just after 30:30. Then we can go into our next session. Thank you very much for the good discussion that we had.
Text heavy those. Probably do.
To you.
Then it is. I mean, that's the issue. It is easier. No, I know, but like. Yeah. Just like that's
Yeah. Thank you. Now we're going into our second technical session of the day. It's broadly under the theme of global design, and we've got two very esteemed speakers and some. So starting us off is see Dr. Michelle Johnson, but I see you're an associate professor, so I suppose she'll be trying to do it. Dr. Michelle Johnson from University of Pennsylvania. She runs the robotics rehabilitation lab, which is under a bigger grasp lab there, and yeah, she'll be talking to us about
First, I want to thank you guys for inviting me. It was a privilege to get invited to ICRA at Ford in Africa. Just a little bit of background. My PhD is actually in mechanical engineering. Actually, all my degrees are in mechanical engineering. I went to the University of Pennsylvania as an undergrad. And after that, I started doing robotics in my master's program at University of California. And then somewhere along the line, I discovered that you can make robots to support people with disability. So in my master's program, when I discovered that that was a thing, and it was a new thing back in 1994, as I date myself, I realized that that's the type of robotics that I want to do. So I ended up moving to Stanford University and did my PhD there in mechanical engineering, but with an emphasis on kind of biomedical applications, and essentially been working in the space of rehabilitation robotics since then. So that's kind of me in a nutshell. I kind of want to give a little bit of a motivation for why rehabilitation robotics, talk a little bit in brief terms about it, and then why affordability is something that one of the pursuing, and then talk a little bit about how we're trying to realize affordability in the context of kind of a global penetration of rehabilitation robotics. We have some financial disclosures. All we need to say, one of the systems that I'm presenting is something that we're trying to commercialize under recuperable robotics. So from a global context, and because I know there are primarily roboticists in the room, and I'm not sure who's into healthcare or not, so I'm gonna lay a little bit of foundation so that we're all on the same page. So the rationale for kind of increasing the use of technology within this realm is the fact that non-communicable diseases are only increasing. The biggest ones, biggest NCDs are cancer, cardiovascular disease, and stroke. And I just highlighted heart disease and stroke. I got my start in applying rehabilitation robotics to stroke survivors. And I kind of give you a little bit of a sense of what happens to, so stroke, just to give you a little background, stroke is like really one of the major cause of adult disability in the United States and worldwide. And it's only getting greater, and I see more and more evidence within global spaces, especially also in Africa. Now, for example, in Botswana, infectious disease and stroke are so in the US, there's 800,000 per year. It's a $56 billion issue, and most stroke survivors end up living 25 to 75% of them will be living with some type of disability in their upper extremity, their lower extremity. So you'll find that a lot of rehabilitation robotics are possibly focused around neurological impairment, such as stroke, brain-induced motor and cognitive impairments, such as stroke. Just to give you a sense of, this is a complex human in that because we often work with people that are living with impairments, we realize that the robots that we design are not kind of like, you can't make assumptions as to how the robots will always interact with the patients. They may have a cognitive impairment, 61%. Some 65% may have some type of motor dysfunction. maybe there's psychosocial issues, and many of them might have issues in activities of daily living and how they live their regular lives. So let's pull back out of the US and think worldwide. The growing number of people, and as you get older, stroke will increase, the prevalence of stroke is increasing. At the same time, there's a shortage of people to take care of them. And these persons might be clinicians, it might be their loved ones, it might be nurses throughout the area of how do we take care of people with disabilities. So what we find is that there's a gap in care. And this gap in care, I think many of you saw that during COVID when we saw how rapidly people were getting ill and there were not a lot of doctors, et cetera, equipping them. So because I'm an engineer and because I'm a roboticist, I think, okay, we can build technology to help bridge this gap in some way. And that's our kind of goal and motivation. The type of technology I'm talking about, there's an area called therapy robots, assistive robots. And therapy robots, when we think about those, they're about remediation, trying to change the way we improve the recovery cycle for someone with an injury. So for example, if you have a stroke and you have an upper extremity and you have maybe weakness or some type of paralysis, the robots there are designed to help maybe lessen the weakness, reduce your impairment so you can do more. So that's the idea of therapy robots. Assistive robots, however, come alongside. So these are robotics like prosthetic robots, exoskeleton robots. These are things that are designed to function within your regular environment. Basically, take someone who has an impairment out of their home and into their community. So those are the two main categories of utilization robotics that you will encounter. So it's a big deal to say where are these robots functioning within the healthcare system. And the ICF classification, if you're not familiar, is a common healthcare classification of how we should think about disease and function. And when we're developing therapy robots, we can develop them on many levels. We can develop them from a perspective of how do they interact with a body part. For example, if there is impairment in terms of range of motion on the elbow, maybe that's the body part that we're going for. If there is an impairment in the way you might flex your ankle, for example, stroke often results in foot drop. I now may think about a robot that will be focused on ankle and reducing the activity impairment there. So the robots in these measures can't just be functional. They must be therapeutic, or they must have an impact on activity, and they must have an impact on participation. So it's not just sufficient to design a robot that functions. Does it function well with the human that you're targeting? And does it result in any remediation or improvement in terms of their activity or their participation in their lives? The assistive robots are in the same space. You can design them as small systems, targeted systems on body parts, targeted systems for supporting function, like robots on wheelchairs that are manipulators, or you can design them to enable participation, like Pepper and social robots that you see out there. So in our lab, we're really interested in stroke and neurorehabilitation as kind of the context of how we might develop some of our key therapy robots. So I work very closely with occupational therapists, physical therapists, studying how human-human interacts so that I can kind of figure out how I should design these robots to support the healthcare environment. And I think one of our first speakers said, your robots will be rejected if they actually make the environment more difficult. So one of the key design strategies is studying how are they operating now, and so that you can figure out how to insert your system within that context. Oftentimes, when we're observing, we're looking for three main things. We're looking to understand the kinematics of movement, how the therapist is interacting, how the patient is supposed to be moving, and then we're looking at what are the trajectories involved so that we can maybe design trajectory optimization functions so that we can actually support the movement. We're also looking at interaction forces. We're looking at how are the therapists touching the patient, pushing the patient, lifting the patient, and things like that, so that we can kind of define the force feedback interaction between the robot and the therapist. And then also, this is where the social robot part comes in, is that sometimes it's not just sufficient to have a functional system. You need to also think about the intent. What exactly is happening? And this is where I was really interested in the whole language LLMs, because I think this could be where those would be great integration within the structure of rehabilitation robotics. But thinking about why is the movement happening? What are the cues that are going between the therapist and the patient? And then what are the responses that need to occur? I did a study where I worked closely with an occupational therapist to kind of, and her students, to define this in a kind of like a high level way. And then what we did was we then took out roles that we observed. And these were some key dyads that we saw in the therapy process. We saw therapists demonstrating something to their patient. We saw then the patient observing. And so then we saw what happens then is maybe the patient did a movement that the therapist wanted to correct because maybe it's not safe. And so the therapist asked the patient, you demonstrate and let me see. Now they're the observer, the patient is the doer. Something happens in the motion that the therapist feels that they need to come in and help, and they change their roles, and now the therapist is the helper and the patient is being helped. So we noticed that these three dyads seem to happen. So they're almost like state spaces. You're functioning here, something goes on, and then you switch roles, and then there is a combination. So what we thought about is, how does this map onto how we want robots to interact with humans in these types of scenarios? So this is probably one of the earliest therapy robot systems that I worked on in my lab. It's called the Activities of Daily Living Exercise Robot. This is an example of a helper robot where, in this sense, we're permanently always connected to the individual, guiding the movement. So this robot might be sensing, doing some type of observation, but it's not a hands-off way. It's always connected. There are force sensors, there are encoders, we're kind of collecting this data with the hope of designing these trajectories to support recovery. Let's step back and think about what are people doing. In those three dyad roles that we saw, they're colleagues working on different aspects of it. We see the demonstrator robots. I worked with a colleague on developing and using the Baxter robot as a demonstrator for people who have elder patients and trying to get them to be more like an exercise-friendly social robot. So demonstrating movements and activities, and then creating games that the robot can execute, and then having the patient follow those games. So those are examples of robots that are essentially maybe observers and demonstrators. We also worked on kind of integrating Vigo and telerehab, and I'll revisit this case where we're thinking now the robots are observing and demonstrating. The humanoid is used to do the demonstration, and then the patient is working in concert with the therapist on the other side to do the work. And then the Adler robot that I showed you is the helper robot. But most of the robots that are existing now in rehab spaces don't do all these three behaviors. They maybe do one or two, but they're not kind of working the way healthcare personnel works or with the way therapists work, where they're fluidly moving between these two characters, these roles. And I think that's one opportunity in terms of development in the future. I always like to say this because everyone have a little bit of different philosophy in how they design rehabilitation robotic systems. My philosophy is that we should never be taking the human out of the loop. That the therapist is, or the clinician, or the caregiver, or the MD are a fundamental and critical aspect of the relationship. And so our robots, while we might want to make them have different levels of autonomy, fully autonomous to semi-autonomous to completely controlled, that should be a choice that is given to the therapist or the clinician. So if the clinician wants to make the robot that's within this role fully autonomous, they can choose to share this autonomy, or they're partially autonomous. The therapist does something and the robot does another. So my philosophy should always be these human-robot interactions should always require shared control between the clinician and the patient. And over the 20 or more years that I've been doing this, one of the things that you'll find is in integrating rehabilitation robots into the healthcare system, this has always been a tug and war. There's fear there from the therapist standpoint or the clinician standpoint that say, well, is the robot trying to take my job? Right? That's first thing. The second thing is when they don't have control, they worry about the safety of their patients. That's number one, is their patient. And so if we can design robots that have a little bit more shared control, where the therapists or the clinicians have the ability to program it the way they want to, then we're going to be a little bit more successful in terms of getting them to be used in healthcare systems, no matter where they are. So over the years, I think some of the first rehab robots for stroke came out of MIT and in my lab at Stanford. And over the years, more and more people have gotten into the field, and we've built some evidence as to their effectiveness in terms of reducing impairment and improving function for stroke. And these are different systematic reviews. And I deliberately picked kind of like how there wasn't much happening in 1980, but around 1990s, where I say that the field started, we've seen like an explosion of application areas within this space. I used to go to ICRA and feel like no one is caring about healthcare, to now going to ICRA and finding lots of people, which is really good though. What are some of the pros? I would say they're enabling autonomous or semi-autonomous training. What's key is that therapy and clinician kind of engagement with patients can be really intensive and fatiguing. So, and then it's also very subjective. So when we can provide a system that can provide consistent, repeatable, and intensive information, or also objective measures, and feed that back to the clinician, those are really good things. And that's actually what robots bring to the table. They don't get fatigue. If you want them to move the limb 1,000 times, that's what they're going to do, and they're going to do it the same way the whole time, unless, of course, you design in some learning and where the robot might be adapting to the patient. So one of the key goals as we've gotten over time is I've been thinking, and I think the idea of the humanoid in my home, that was always like our vision, that we would then have these robots seamlessly integrating in our everyday spaces. But we're literally lagging behind that. And what we see is, where are these rehab robots actually existing in terms of, and how have they penetrated the healthcare markets throughout the world? So I got together with my clinical colleagues, and we created this book, and we curated this book where we wanted to look at this question: had rehabilitation robots for neurorehabilitation in high, low, and middle income countries. So we invited a lot of our colleagues in different places in the US. Sorry, I didn't know anyone in South Africa at the time, so you were not represented in the book. But to talk about like this aspect and how robots were they being uptaked in their environment, and it's a really interesting book. And we also looked at systems or where like people were developing robots, creating startups, putting robots, where were they accessible? These were some of the common places: South Korea, Germany, USA, Canada. And then in low and middle income countries, we saw a few places like Iran, China, maybe India and Turkey. So the upshot is majority of the activity is happening in Europe and in America, and some in Asia, but very little is happening in Africa and in some parts of South America. A more recent graph, as they showed that the rehabilitation market is actually growing since 2015. It's now a $26 billion market, but none of that profit is coming to certain places. The low and middle income countries, very rare benefiting from. And if they're not benefiting from that, they're also not benefiting from the advantage of possibly having these systems within your healthcare structure. This is a better view that kind of talks about high uptake versus medium and low. So this is a more updated version of kind of where and what's happening in terms of these neurological or neuro rehab devices. A colleague from Nigeria was looking at specifically at stroke and saying, what are some of these pragmatic solutions that would allow these systems to penetrate low and middle income countries? And one of the things I took this quote from their work that says, robots are not affordable, but despite their high costs, they have some kind of advantage, right? That because they could be automated, they might be able to deal with the fact that there might be rehabilitation shortage in personnel in countries like in low and middle income countries. And so may be able to require minimal input from the therapist and therefore save in time and effort. So just to think about, well, what is the state of rehab robotics in low and middle, or rehabilitation in general in low and middle income country that might have inspired that statement? A couple of things to know. Rehabilitation seems to be afterthought. And many of the countries that we surveyed in the book that were low and middle income, they would have a robust curative strategy, a robust, some robust preventative strategy. But when it came to dealing with quality of life issue for the person after a stroke, it was an afterthought, or it was just the infrastructure was just not there. So what we see then also are marginal resources spent on the rehabilitation services for many of these countries. That means that the number of skills therapists and people who can deal with are much lower. This is kind of a density of physiotherapists per population. You'd see that much lower in the Eastern Mediterranean and African region. And these are critical service groups for people that are living with disability after disease in general. The shortage of staff, remember it said that maybe the robots can pick up that bridge that gap by picking up some of the work. And if they're somewhat autonomous, they might be able to also support the therapist, or also maximize the ability of one therapist to treat many patients. So these are some of the key rationale as to what's happening in rehabilitation environments that actually might be the reason why these rehabilitation robots haven't penetrated low and middle income climates. The world is also recognizing this. There is a manifesto called Rehabilitation 2030. And one of the things it's saying is that more and more our population is growing older. We need to start not just thinking about saving people from the disease, but also saying, how do we make sure that people's quality of lives are also improving? And I think this is really the opportunity for rehabilitation robots. It's not inclusive. So in my head, if we can't get these robots everywhere, then we need to kind of think about, well, how do we get them into these low and middle income spaces, not throwing away what we know about their efficacy, but how do we make them attainable? The problem with a lot of current systems they may cost $100,000, $150,000. They're often mechanically complex. We talked about motors at the core. The more motors you have, the more complex these systems might be. They're huge in sizes. You find that a lot of rehabilitation spaces in low and middle income countries are constrained by size, and the cost is prohibitive. So they're not successfully bridging the gap. So one of the thrusts of my lab has been thinking about affordability and how do we build more affordable robots that still have the advantages that we see in the more expensive systems. Natural question is, what is affordable? Things that we've been thinking about as we had worked with colleagues in Mexico, we worked with colleagues in Jamaica, and then more recently we've been working with colleagues in Botswana. And the idea that the World Health Organization kind of gave us a sense of what this could be. When they think about cost-effective strategies that are implemented beyond high-income countries, they're thinking about the gross domestic product per capita. And they use that as kind of a guide. So something is highly cost effective. We're assuming that that we can maintain the benefits that we know are possible by rehabilitation robots. And so that the benefit and cost ratio and all the other pieces that now we're matching this ratio, that if you're less than the GDP per capita, then it would be a highly cost effective potential solution. If we're between 1 and 3 gross domestic product per capita, it's going to be a cost-effective solution. And then greater than that would be unreasonable, greater than 3 times the GDP. It's really unreasonable to expect that this technology could be really feasibly used within a country. So just as an example, because I've been working in Botswana, here, the US GDP per capita is 65, that's 1. Multiply that by 3. And so we might expect, many of the hospital systems and the healthcare systems, whether public or private, could possibly pay for a $200,000, $150,000 rehab robotic system. In Botswana, we're seeing, the GDP per capita is 7,000, and 3 times that is 23K. So that then we're arguing, is that if I want to buy it and I want to put it and then bring that system into Botswana, is that cost effective in terms of how I'm going to deal with the population or deal with rehabilitation? And the answer would be, and there are instances where people have, for example, there's a case in India where they purchased one of these Locomat type robots and they brought it into a private hospital because the hospital could afford it. But the challenge was that to use the robot to try to get their money back, the patient, the average person, could not afford to pay for the interaction with the robot. So in many ways, it became, yes, here it's possible, but it's not cost effective. And then the hospital could not make their money back from that investment. So beyond myself, there are people trying to lower the cost of rehab robots. I just want to give some examples of what these might be looking like, from assistive to therapeutic robots. And the idea is to get them below certain thresholds so that they could actually be possibly purchased by a hospital system in a low and middle income country and be usable and be profitable if from an income stream, or that they could be used in someone's home environment in primary care scenarios in the area in the system. We also did a review where we tried to talk about, well, what else is happening specifically in developing countries, low and middle income countries. And we wanted to look at strategies that people were using to actually meet the need and to reduce the cost and to be more effective within healthcare situations. One of the strategies was to use low cost or mechatronic systems, to use systems that come together in almost like a circuit training or a gym type of scenario, but also to think about systems that are modular and that are easily reconfigurable. To use and leverage very heavily 3D material and other soft robotic systems, et cetera, found materials, and to rely on open source in terms of sharing. And I think there were a couple of people or instances where that had been discussed here. And the other strategy was to use local manufacturing techniques along with kind of taking that technology and redefining it. So what I want to do is kind of talk a little bit about some affordable design strategies that we've used, and by kind of talking in terms of case studies. So I'm going to focus on a couple of cases where our goal was to use low-cost system or mechatronic system, to use cheaper material. We leverage a lot of 3D. We leverage some of the commercial systems that might have been available to build more complex systems. These are some examples of the systems that we talk about. I'm not going to only focus on stroke because our lab actually have branched beyond. So my lab is focused on supporting adults or children or infants at risk for motor delay during a brain because of a brain injury, or adults that have a brain injury. So we're looking at across the spectrum. So first case study, Mexico, working with some colleagues in actually a tertiary care rehab hospital there, and working to try and understand, can we bring in a system of technology that could support allowing one therapist to be able to treat more than just one-on-one strategy, almost like a robotic therapeutic gym. Our first attempt was to take the system that was in my lab, and in this case, the idea was to leverage haptic wheels, force feedback wheels, and serious gaming, and doing that together. So first thing was to take what I had in my lab, and they developed a version of it in Mexico, utilizing local resources, as many things as they can find within the Mexico system, and then create this very mechatronic system. There, clearly, we then took this system and we got a grant to create what we called a technology gym, and we had variety of different technologies, and the idea was a comprehensive gym that could treat a stroke survivor who had both upper extremity, lower extremity, foot drop, and a variety type of, and even cognitive impairment due to their stroke. What we envisioned is that there would be an engineer type technician that would be trained on repairing and fixing the system. And then we envisioned that a clinician would first evaluate and determine what type of circuit training might a patient do. This strategy, we set our limit at 29K, just below the 3 GDP threshold for Mexico. So we were kind of cognizant of that. We actually ran a study. One thing about my lab is we focus on building systems, but we also focus on putting them to work with humans. and with the population that we want in terms of disability or impairment, and trying to validate that they're doing what we designed them to do. So we had, in this case, ran 20 stroke survivors through the system. 10 were randomized. They were randomized to either getting their treatment through the gym or getting their treatment one-on-one with a therapist. What was important, though, is that we didn't want to reduce the care. So we collected some data about the cost and whether we were able to keep motivation high while we delivered an actual reasonable product. So our strategy was thinking about cost minimization. Is we wanted to compare the cost of using the therapeutic intervention to the cost of providing one-on-one therapy. What we saw, so this is actually a review paper that picked up our study later and looked at the fact that with our study, we were able to drive the cost down, and in the robotic group from 19.2, let's say $20 USD in terms of treatment to $7 USD. So we were able to do what that quote said. We were able to maximize the impact of one therapist on the ability to treat 6 patients at the same time. And that fundamentally, the strategy of having this type of system and these types of robots or these type of therapeutic systems within this context would be feasible and reasonable. One of the things we learned from Mexico was that we couldn't, the simple force feedback wheels were not sufficient when we think about very severe stroke survivors who had really hard time moving their impaired limb. And so it required force feedback or forces to help move their limb beyond what these mechatronic simple systems required. So we set about to develop a 1 degree of freedom robot that we could reconfigure in different ways, so we could mount it horizontally and vertically. We wanted it to be simple, and we wanted the idea that these robots could be used in this type of circuit system where maybe you had the version that is horizontal here, the version that is vertical, so you could work the entire upper extremity. That the end effector on the robot could be removed, redesigned according to what we need. We had force sensors in the handle, simple encoders, and this robot our goal was a $2,500 system that could then be used, and then we would leverage serious games in order to create a strategy. This is a system that we're trying to now commercialize, and these are kind of like our evolution. We have an NIH grant that is kind of helping us to take that idea to then create something that could be usable in a hospital environment, in a community-based rehab setting, or in someone's home. So this idea of trying to target a system that would be under that threshold, that would be reasonable, that could be used in those 3 main hospital or therapeutic settings. Our other strategy is telerehabilitation by design is a great strategy to save costs, right? And so we saw a lot of that during COVID, but what we also saw in COVID was that when you only had telerehab, people that were severely impaired who needed someone to come in and work with them were not able to get services because they were able to have like a connection, but they were not able to have the actual movement of their arms or the intense exercise that they might need. Or they were confused by, a lot of older people were confused by the screen. What were you asking me? What was going on? And so one of our ideas was to develop a social robot augmented by telepresence to see if such an affordable system could be used for stroke rehabilitation or working with children, working with the adults, etc. What was our design strategy? Our idea was to think whether leveraging the pluses of a social robot in terms of motivation, increased interaction, but keeping the human in the loop through the telepresence video platform, can we then create a system that would be usable within the rehab spaces? We actually used a Kabuki commercial system that was relatively low cost. And on top of that, we built up the humanoid robot, leveraging mainly 3D printed dynamical motors. I mean, we were trying to go relatively low cost, but relatively effective. And we also had a touch screen that allows for the therapist to be able to dial in and observe the movement while it's occurring. So we also designed the face where we could make it emotive so that we would have different faces going on. So all this stuff we built, my student developed here so that we could kind of have driving that cost down. At first we were using a Now robot, but the Now would be a higher price point than we wanted. So that's how we ended up building our own. This is some of the degrees of freedom that we implemented into our robot we call Flow. And then the therapist is able to control the movement of Flow, whether joint by joint or a series of tasks that the robot could do while they're interacting with the patient. There are cameras that allows us to pick up some of the information, because this is now the classic demonstration robot. It's an observing and demonstration platform. Just play the video so if there's no sound, couldn't get the sound to work. But this would be the idea that the therapist is in another room, co-located, maybe someplace else in the hospital, or they're at a main hospital. The robot is at a rural environment where the patient comes in, and then the therapist is essentially driving the robot, passively driving the robot around. This robot is not fully automated. It's fully controlled by the therapist, so that the therapist drives the robot in the room, for example, and one of the encounters was the therapist asked the patient to name the robot, to talk to the robot, and then do particular activities with the robot. We're also kind of thinking of like the next phase of the robot. So this is kind of some of the another version of the system that was lighter weight. In trying to do some experiments with the system, we created kind of several variations in terms of how you would use the system. We wanted to test if social robot augmented telepresence was indeed effective in terms of, and whether patients would accept it, and whether therapists would also accept it. So we kind of created a study in terms of the use of this system. Won't bore you with the results, but the key thing is, if we're going to develop these systems, especially within the context of disability, we must evaluate them, or else they're pretty much not. They're useful as teaching platforms, but they're not going to be useful as healthcare platforms. This is an idea of some of the experiments that were run, an example of the robot playing target touch, where the idea was the therapist wanted to observe the movement of the upper extremity, the bilateral movement as the unilateral movement. And so the robot, you can't hear it, but it's asking the person, touch my right limb, touch my left limb. And then in this version, there was a Simon Says game where the robot would say, can you repeat a certain activity for me? I'm going to do this with my arms. Can you follow? and then the patient is following, the therapist is observing, and they're able to then do some diagnostics. Some of the diagnostics that we implemented essentially leverage some ML, open pose estimation activities, as well as, but what was important was that there was real time subjective evaluations that the therapist is doing based on the traditional tele-rehab, but we're collecting the data and trying to do, and our goal was real-time objective evaluation, and that's something that we're still working on. So one of the phases that we've been thinking about is working with stroke survivors that have both motor and cognitive issues. Social robots are potentially a really great system to use with people with cognitive issues. And so we're trying to study using EEG, what is, if it's worth dropping a robot into a telepresent platform, how is it connecting the brain activity to the motor activity that they're doing, and also trying to we're trying to provide some evidence that suggests that if you substituted the flow robot in a community-based setting, that you're going to get some of the same advantages of if it was a human. So needing to prove that that this strategy is feasible. So this is kind of one of the things that we're trying to do, and I think the robots, we're doing these with videos of just watching videos of the robot, but then there's a theory as to whether embodiment makes a difference in terms of rehab. So we're also looking at whether you're observing a real robot doing the activity versus a video of a robot doing activity. Does that make a difference in terms of your EEG signatures? The other idea that we've been looking at here, I've been kind of thinking through affordable mechatronic toys. So now we're talking about adults, now we're talking about kids and infants. This is a huge issue in terms of early diagnosis of motor impairment. This is a worldwide issue, and in particular a problem in Africa where the cerebral palsy or kids go basically unmonitored, and their development is then suffers because no one detects that they have a motor delay or potentially cerebral palsy. So looking at diagnostic screening and creating systems that allow us to measure and what's happening with the baby is something that we're working with our children's hospital to do. The robot you see here, well, the mechatronic system, has IMU sensors, pressure sensors. There are cameras in the Panda gym. I'll just do where you can see the evolutions of the gym, and there are cameras in the gym that allows you to observe what's happening with the child. Both the child plays by themselves or with the robot, with our toy. We also use pose estimation here, where we're trying to basically recreate what we see happening with the infant, and then processing kind of in MATLAB. There is a force plate on the bottom, so the baby, we're collecting center of pressure data as the baby kind of plays by themselves, or we do this also with the toy. One of the things that we found was that our toy had some limitations. It wasn't smart enough. So now we're trying to merge ML techniques with the toy. We've developed our own sensors, like a lossy sensor, where based on, we can manufacture these sensors a little bit more easily. We were using FSRs before, but they were just really touchy and they were not reliable. So we're developing kind of a different type of sensor so that we can have maybe more reliable information as to how the baby is interacting with the toy. Combine that with machine learning techniques to try to classify what type of interactions are happening so that we will be able to have a better Okay, sorry about that. Something's going on with the screening. So that we can kind of have a more active or more interactive type information about what's going on as the baby plays with toys. There are two types of information that's important. Early diagnostic before the baby even is aware of a toy versus voluntary movement. So we're able with this play gym to think about how can we assess and use these mechatronic systems to really give some information about what's happening to them. Just a quick note is we also developed a robot infant simulator. One of the things we realized, it's really hard to get the babies to do what you want them to do when you want them to do it. And so in order to really truly investigate the signatures of what we were seeing in terms of center of pressure movement, in terms of their trunk movement, one of my PhD students is kind of working on a robot infant simulator that allows us to move the arms, the legs, and the trunk with the goal of being able to pop this simulator within the context of the gym and collect some data on and mimic essentially some of the movements that we see babies doing so that we can then kind of like repeat that movement and really understand what are some of the movements that are causing some center of pressure changes? What are the movements that are causing? How important, for example, is the trunk in terms of predicting motor delay and things like that? Okay, so I'm gonna wrap up. Robot, how would we do that? As well as if we had two of those 1 degree of freedom systems, how could we leverage multiplayer gaming and behavior strategy where now we're thinking of connecting robots haptically as well as virtually to improve the rehab outcomes. From Mexico, this was kind of an inspired system where we'd have a circuit of a variety of different robots. The idea was first we had to develop assessment tasks for motor and cognitive. I had a PhD student looking at how do we precisely determine the therapy needed depending on whether someone was cognitively impaired or motor impaired or both. And we started doing this because we started working in Botswana, where the stroke survivors, about a third of them also had HIV. And when our lab started, we knew nothing about HIV. And so we had to determine how does the strategies that we've developed all these years with stroke, how does that map on to someone who now has HIV as well as stroke? One of the things that we've discovered from some clinical testing that we've done in Botswana is that people with HIV have mainly more cognitive challenges and fine motor issues. And if you add stroke on top of that, you exacerbate the motor issues, but the cognitive challenge can be exacerbated or stay the same. So we're then had to develop some assessment strategies that we could use with the robot to detect who was in these different categories so that we can then adjust the therapeutic strategy with the system. This is where we're working in Botswana. We're working with the University of Botswana, the Botswana UPenn partnership. We built a rehab lab there, and the idea, we've also built a couple of robotic systems where we're looking at the 1 degree of freedom platform with the 1 degree of freedom robot. We've placed one in the major city of Gaborone, and then we placed one in a rural environment in a district hospital. And the idea was to kind of evaluate whether these systems could be used and whether the clinicians could leverage them in real time. So this is just an example of some of the patients that were from Botswana utilizing the system and us running some of the therapeutic tasks. In terms of reconfigurability, the idea that we're working on right now is one robot, one system that could be used as prismatic only, 1 degree of freedom, 2 degree of freedom system. That is go from a planar robot to bilateral and to a more complex system that is still in Cartesian 2 degree of freedom, but now there are like five joints involved. The idea in working with our colleague, that's why we call it Penta, because Penta is kind of more of an Italian way of putting this together, is that right now we're trying to realize this system in a relatively low cost way so that we can then map that into our lab in Botswana, and then we can test whether, the utility of this particular system. One key thing that we were realizing is how do we drive the price down, and what actuators should we use? We first were starting with Maxon actuators, and those are quite expensive, as most of you probably know. And so we're going to then add multiple actuator systems, and we're driving that cost up even more. So we started then also working with a colleague to develop quasi-direct drive systems. He's developing those systems, and we're trying to see if we can substitute those motors for the typical brushless Maxim motor. This is just a picture of the 1 degree of freedom system there, and now we're in the process of developing the 2 degree of freedom one. Just want to kind of point to, we have actually really some good specs in terms of the amount of forces that we can do as well at reasonable cost. I know when you try to do the math and you transfer it into Rand, it might be still expensive, but the goal is to drive the cost down as low as possible. We're now working on the PR configuration. We've done simulations on what we expect it to be, and then what we believe the type of forces that we can generate. Because remember, in rehab robotics, it's the human robot interaction is important, because if someone is severely impaired, you might need the robot to do a lot of the work in terms of moving the limb. And if someone is less impaired, you don't want the robot to do a lot of the work. You want to dial down the assistive forces and then maybe increase the resistive forces. So the therapeutic strategies are very important in terms of driving recovery. If you're interested in the quasi-direct drive motor, the colleagues that I'm working with have been trying to drive costs down while keeping the torque high. And in terms of a possibility of having a cheaper motor, but that's still strong and able to support human-robot interaction. I know time is not on my side, so this is just my student that's been working on haptic connections, virtual connections between two simply designed robot, but how do we maximize their impact by using the other person to challenge each other in this type of dyadic atmosphere. This robot uses those quasi-direct drive motors that you saw. And with the quasi-direct drive motors, we were able to remove the gearbox and really drop the size of the system from the size of the system was now in terms of the portability of the system increased a lot. This is kind of an example of they're playing a game. There's actually a partition between them, and they're playing the game, the same game virtually, but what the person doesn't know is that the forces that one person can be felt by the other. And so in a way, we can design the controller so that we're challenging the person in different ways. And we're now trying to determine, does that improve motor learning in the rehabilitation context? Last thoughts. I think if we're going to achieve affordability and increase the use of these types of systems in low and middle income countries, we really need to focus on these areas. How do we decrease the complexity of the mechanical design, leverage the relative low cost of now computers, et cetera? How do we deal with power? We have not touched that, but power is an issue. So, especially intermittent in Botswana, sometimes we lose power for no reason, or like a Wi-Fi connection. And then kind of how do we rely on that? And then by leveraging ML. As you guys are trying to do ICRA at 40, I want to draw your attention to the fact that we're trying to do something and increase the rehabilitation robotics activity in Africa. So I'll keep in touch about that. And the hope is that maybe there will be opportunity to convene a rehab robotics type focused conference in someplace in Africa. We're thinking about that. All right, thank you.
Thank you for that. Thanks for the talk. Do you have any quick questions from the floor?
I have a potentially unpleasant question is, how do you measure effectiveness in this space? Like, if you've got a therapeutic robot and someone with an incurable impairment to some degree, how do you measure?
So usually the impairment's not incurable. And clinicians have their strategy, because you want this to be usable by clinicians. So they have clinical tools that are standard tools that they use to measure levels of impairment. So for example, if our goal is to take someone from severely impaired to mildly impaired, we can quantify that. And if there's stroke, there's special assessment tools that are focused on stroke. And if the person, for example, has multiple sclerosis, you use a different tool. If the person have HIV, you might use another. So one of the ways to validate is when we develop these systems, we're trying to make sure that the objective measures that we get off the robot correlate, and that it can predict clinical. So we, one of the ways that we published on is looking at the assessment games that we do, quantifying how someone with low function what's their motor performance versus someone with higher function. And then can we predict it, and can we correlate highly with the clinical tools that they're using? Challenge for us as roboticists is that the clinical tools are kind of flawed in themselves. They have high ceiling effects. And so what we're saying is, if we can at least show that there's a high correlation, that we can predict these clinical tools, and then we could show that when we use the system, we drive down impairment and we see the change in the clinical tool as well as on our objective measures, then we validate the system.
So you spoke about how for the 1 degree system, whereby there might need to be some sort of assistant force or torque, or resistant force or torque. Is there a way to that the robot kind of takes in a certain value and then from there feeds back and says, okay, actually we're going to have to decrease the resistance or increase it, or do you need clinical help?
Good question. So there's a concept, a control strategy we call assist as needed. And that strategy could just be based on the force torque sensor that you're measuring or the goal that you want the user to accomplish. So for example, if you want them to move from a position close to the body to a position away from the body, we kind of map that trajectory, right? And so we can look at their their position forces over time? Are they doing what you want them to do? And if someone is impaired, they're not moving towards the target goal, then you might need to augment the forces, the assistive forces. If someone is moving really quickly and they're not having any trouble, and you have kind of like a desired movement profile, if a person is meeting those profiles really quickly, then you know, this person is much more functional than we realize. We now need to dial up the force resistance so that now maybe the focus is not on assisting, but on resisting and building strength. And so this is actually a new place that the field is going, is thinking about multimodal information, understanding, for example, how do we measure in real time what's going on with the patient? We've used EMG, kind of measuring muscle activity in real time, galvanic skin sensing, the measuring stress in real time. Are people dealing with stress? We've also begun to use video emotional evaluation. So now in the field, it's kind of how do we integrate all this information to determine how the robot responds from a control standpoint. So this like adaptive treatment strategy is definitely a part of the area.
So just for the benefit of time, I think we are having a really rich discussion, and there will be multiple opportunities over lunch and over the rest of the day to get those questions asked. Thank you once again. Just as we get set up, I'll introduce the next speaker. Prof. Brian Stockton, from the University of the chair of robotics regulation and control systems. Looking forward to the insights that you're going to bring.
Hi everybody. I'm going to be talking about the history of robotics in South Africa, specifically past, present, and future. And so I've got different hats that I'm wearing today. One is the chair of the Joint Chambers of Robotic Automation and Control Systems here in South Africa. I really think this is a great initiative. It's we actually need to have more, see what other people in the country are doing. We need to be able to see who can be our examiners, who can be our viewers. We need to elaborate something. Discussing a lot of that stuff today as well. I'm in a smart lab. So a lot of the supervisors over here will tell you don't need to be bright and have bright marks to be able to do research. You need to be smart. So, and then University of KwaZulu-Natal, which is quite important apparently for this event as well. I'll discuss that later. As well as with Nelson Mandela University with the advanced engineering design group over there. So I've got different hats on at the moment. Before I continue with that though, again, I must just thank the organizers for this. From ICRA's perspective, I really think it's great that we're having this and a lot of effort goes into this. It seems like it's just a few presentations that you put up over here, tea and coffee that's been served over there, getting the caterer to do the lunch. It's a lot more work than that. If you've organized a conference, then you know it's a lot of work. So yeah, thank you very much for all the effort that you guys are putting in. I've been in so much email contact with people I don't even know faces and names type of thing. So I'm going to start learning people's names and faces and things in the next couple of, well, at least for today still. And hopefully also, I think I've even been examined for a lot of people over here, and I don't even know these faces are over here. So I'm really open to get more interaction over there. Then, yeah, ICRA at 14. I was 20 years old. What did that mean? Well, it started off, it was born in 1984. So let's just see a show of hands. Who was born before 1984? It's not many hands we've seen over here. Maybe, not even. So it's already going for a long time. And this is, quite an achievement. We even think that robotics was considered that. It's quite good. So, yeah, I'm going to start with the disclaimer. And I'm told that if you have a disclaimer of that, you're not going to be offending anybody, but you're going to be offending somebody. So, I'm not here to offend anybody. That's not my goal. Is make you think. Just rethink about things in terms of your research. I support all the research you guys are doing. So it's not like I'm thinking that, this research is not good or that. I support it. So I'm not saying it's good. It's not good. I've made these mistakes myself. And so I'm trying to sort of say, well, I've had to try and learn from my mistakes. So hopefully you'll be able to also just, look along those lines. And I've shown some of the research we've done. For copyright reasons, you don't really want to show other people's stuff because it can be offended sometimes. But this is not all the research happening in South Africa. Okay, so before I start off with things, yesterday was Heritage Day, and we got told we need to wear our traditional clothing, which made me a bit confused because, I've got French blood in me. I've got Irish blood, Scottish blood, Dutch blood. Pavement special becomes a sort of a word that comes to mind. It's you're not really knowing where your identity is. So then I thought, okay, well, we're going to be going to this what was it called, the Sedi Cultural Center. I'll be able to find my roots over there, where I'm coming from. Apparently, I'm related to Shaka Zulu because I stay in KwaZulu-Natal. So that was sort of one thing that was sort of a good gesture. And then eventually we went for the traditional African cuisine. And if you were there last night, what was the first dish that you dished up from the selection of food over there, or the African food that we had over there? It was pasta. So apparently Italian as well. So it's and the reason why I'm bringing this up is that with robotics things have changed over the years. It's not just focused in one specific thing. Things have blended together. You can't say anymore you're from this culture and you're from that culture. We are adapting different cultures. The same thing has happened with robotics. We're adapting different scopes of robotics, scopes of engineering, and bringing that together. So a bit of history. Back in the day, robotics was a nice to have thing. It was toys. You had little toys like this that you could buy. And then there was like some research just started developing. And in the last 20 years, I've been looking at this, how it's made program. And you look at things that were developed like 40 years ago in the industry sector. And that's just things that we were actually researching like 10 years ago even, or at least like I saw people researching about 10 years ago or 20 years ago. As a matter of fact, there's a lot of things that they show over there it's being researched at the moment. Thinking, why are we researching things that are being developed? So you see this invention of, people are trying to get this wheel developed. In the meantime, there's a whole pile of scrap wheels that people have tried to develop and stuff. Instead of just using that power and see what they can make from it, they're trying to go from scratch and basic principles again. So you become a lot of this type of pick up and place robots has been developed over the years. And you sort of have to, if you look at this arm, to get that controlled initially, it's a big task. And that's a very common thing to be able to do. It's not as difficult task as what it used to be. To give you some, some robots were like sort of also really expensive. Innovative ideas, but it is expensive. I mean, we've got Pepper robot over there, which you also heard Michelle talking about. I'm going to be picking on you, but this Michelle, so yeah, again, don't take it personally. But the thing is, great robot. How many of us can afford it? I don't even know if we might have one or so in the country, but that's a reality. This is a search and rescue robot for firefighters. When I did it and built this many years ago, I thought, oh, great, it's going to be used by firefighters and stuff. Finished building it, tested it out. The fire department said, would this be useful? Oh, no, it would be really great. I said, okay, well, why don't you sort of then try and get a few of them? No, we don't have the money. And apparently, the money is so bad. Like if you look in KwaZulu-Natal, where I'm coming from, basically from the north coast to the south coast, there might be one thermal camera that a fire department has got to use. So if there's a fire 200 kilometers away, they've got to first travel, get the camera, travel 200 kilometers, get the fire. It's a bit late to sort of rescue the people over there. So technology is great. You've got the issue that it costs, and that's always an issue. There's a lot of parallel research that's happening. So in 2015, I started the Robotics Centre of South Africa under the Robotics Association of South Africa, trying to get us to collaborate, trying to get us to network together. It's important. The thing is at that stage, everybody was saying, it's important, we need to work together, and yet we're not working together. You don't know what research I'm doing, I don't know what research you're doing, and we're doing a lot of the same type of research. Intellectual property, I think, is a great enemy for us. Everybody's like, it's mine, it's mine, it's mine. But we don't want to share any information, which means that reinvention of the wheel happens. It's sort of having to, the information is not out there to build onto, so we have to develop it again from scratch. And so to give you a typical example, about 2015, I had this endoscopic probe project that we had with students to put down a person's gut and to be able to sort of do inspections and things. At the same time, I was at an institution abroad, and they were doing exactly the same research. And you know what? It's like you actually realize that a lot of the other countries are looking down at South Africa. Oh, you're not able to do research. You're from South Africa, bottom of the world. Yeah, but a lot of the issues that they are experiencing, we've been able to solve. So, I'm not saying that you need to keep in mind that it's not the research we are doing. It's not like everybody's thinking it's low level. It is quite the research that we are performing. Okay, so drones has been a big research topic of the past. As a matter of fact, Stephen Bean still research at the moment. To give you an example, we looked at this drone over here. It's a dual rotor drone. It was quite an interesting project for us to explore because we realized that in the PID control values were different in autonomy mode compared to a manual mode. So we did many tests with it, trying to sort of see how to get that stability going. We also realized that you needed like a counterweight system to get that to work properly. And then we also looked at some research over here with autonomous takeoff and landing with drones, which is also, it's not too difficult to do that if especially with GPS and image processing lately. Deployment of things like, for example, medical equipment that needs to be dropped off at ships. And as the ship is moving, it needs to make sure that drop is going to happen on a ship. And we did it within within a meter sort of drop zone. And then also looking at ways to train a system for autonomous flight. And we actually developed this thing where we could build this into pretty much any aircraft, and we'll be able to maneuver around, get the PID values, be able to do the autonomous flight. And that would be with different crosswinds and weather conditions. And then also coming in for the landing to do that auto flare. So you want to, when you come in land, you want to go for, sort of a good landing. Let's just say there was a lot of nervous people on the plane when I came in, and that pilot needed some auto flaring as well. So there's a lot of research that has gone around with that. Image processing is has also been happening quite a lot in the past. OpenCV's been there for many years and it's still being used. So over here, this that endoscopic probe I was telling you about, we were just looking at ways to identify different spots and things in the gut. This is a sheep intestine that the students did a test on. And so we were able to flush away parts. We were able to, I think you'll even see over here a little clamping tool coming in and sort of to take a specimen sample. So the thing is, OpenCV has been quite a useful tool over the years to be able to do those type of inspections and identification of different parts. Yeah, so there's a tool that's do the sample. So mechanical, you've got in your robotic system your mechanical system, you've got your electronic system, and you've got your software system. These are different aspects that have come together, again, that allow us to build a robotic system. So looking at the parts of some mechanical systems, if we look at this over here, we were trying to go over minibus taxi. Under these wet conditions, we had it remote controlled. And we were able to, when I say remote controlled, we were able to maneuver the steering wheel to autonomously to do these maneuvers that would usually have caused an accident. And we realized with the test that usually, if you do see there was an accident, it could probably be due to the condition of the vehicle. It's not necessarily to do with the, driving or the environment, like rainy weather or so. So we had these dummies inside of it. I wasn't allowed to use students for that. But yeah, and we were able to sort of see how they were maneuvering in the vehicle. Safety belts aren't being worn, so we were able to test that. Looking at the video on the right over there, so at that stage it's going to work. So that stage, this was I think in 2013, we started looking at prosthetic hands. And 3D printing was not a common thing. As a matter of fact, we had to import these 3D prints from New Zealand to be able to, do the project. So John Harris, we got electrocuted by 33,000 volts by tied to our kit to take a cut off from power lines. And he's been doing some tests for us. They're doing really some really great work at the moment, motivational speaking and stuff. But this hand looks really sort of very basic. Wires sticking out everywhere. At that stage, there was a US journalist that said it's the most advanced low-cost prosthetic hand in the world. The thing is obviously you need to then develop and build onto this. It is again, 3D printing was something at that stage. It was sort of new. It was difficult to do. Only a few people were able to do it. And let's be honest now, I think everybody over here has got access to a 3D printer. So that's been something that has changed over the years. Electronics. You look at this is one of those SPIC programmers. I'm sure, I don't think many of you have actually used that, but some of you, maybe if you're like my age, you've used it, or the Atmel STK 500. to program your microcontroller boards. You've got your PCB boards. I mean, we had to go and sit with a permanent marker, draw out the tracks, put into etching solution that will take away all the material over there, sand it off with steel wool. Then you had to draw your little holes over there. And then you could solder the different parts with your microcontroller, and then you could start doing, things. A lot of work had to go into the electronics of robotics in those years. Programming. Assembly code was very common. Start off a little bit of C programming, and yeah, it wasn't as easy as what it used to be, or at least what it is now. It's very, line-orientated programming, which is nothing bad. There's nothing wrong with line-orientated programming, but it was quite a bit of a task to get things working. At present, children are able to build robots. We've got over here the Timio robots. So this was a competition we had a couple of years ago with Switzerland. These robots were actually in Switzerland to replicate a Mars environment, generator had to start off. And we had kids over here in South Africa programming the robots, sending the commands to Switzerland, and the robots were able to maneuver around and do specific tasks. You've got a microbit units that you're able to buy now, and the kids are able to program them. And they're pretty much in UK schools, in many of the South African schools at the moment. So children are able to program them. Obviously, you've got children with arrogance. I'll give you an example. A few years ago, I get a knock on the office door. Student comes in with his mother, comes, sits down. So what have you been up to? Well, this must be somebody I've interacted with quite often. No, been busy. Been building some robots, some drones. So, this is my weekend job. This is easy stuff. In the meantime, he's been using graphics to be able to, program a drone and things. Understanding the integrated aspect of robotics. And so a lot of kids are thinking, well, they can program robots because they're able to do it at school level, and that, it's not actually needs to be studied later on. We've got very much stagnated research happening at the moment. We're expecting robots to do multiple things. I've had our library department contacting me, asking me if we can build a robot that will be able to stand at the door, tell people where to go for, and give them information. At the same time, it must also go and put the books back in the shelf. It must be able to do, numerous different things. When's the robot going to be able to go to a plug point and just charge itself? It's becoming we're expecting too much from robots. A lot of this repetition work of robots not with no purpose. Just picking up the object and placing it again. Things that we've done 20 years ago. And that's why I've got this 404. Also just this repetitive research that we're almost busy doing. And it's hopefully something we're going to be able to, away from. So again, there's at the moment minimal collaboration. Everybody is busy with intellectual properties, all mine. I don't want to share this information with anybody. If you want to do it, you've got to start from scratch. COVID was a good time for us to start putting our heads together, solve problems. There was needed for these ventilator bags and some ventilating systems to happen. I think every single university and institution in the country or around the world basically pursued that. We worked together. None of those products actually really made its way to the hospitals. It just was just a waste of money. But it made us start thinking outside of the box. I know a few hospitals has been in contact with me in terms of these incubator boxes. They have like a negative pressure so that when they perform the operations, the patients with COVID wasn't able to sort of contaminate the staff. We did that with Nelson Delhi University, had some private consultations on that. Funny enough with that, the company was just busy cutting out the pieces for us. They suddenly like just grabbed the idea, started selling it and claimed it as their own idea. Big issue with COVID was that the oxygen tank valves were freezing up. We actually had people with hose pipes spraying them off all the time. So we just developed a water pump system with water at the bottom, spraying water on the top, and it defrosted that. So it started making us think outside of the box and, solving problems that weren't really necessarily in our field, but they were important to do. Okay, so drone research and image processing. OpenCV is still being used to be able to identify people, parts, different shape objects. There's new image processing techniques that have developed over the years. And then for drones that will get used to go and do these inspections. And so, of course, he's going to be talking next about his drone that he's been looking at. So I'm not going to go too much detail about it. The question is that a lot of research happening at the moment is having a drone to do image inspection on different things. Why do you need to build a drone to do the image inspection? Surely the focus should be on the image inspection, getting that solved. Implementing on a drone, that's just a sideline sort of thing. It could be on any vehicle. So, drone research has been going along those lines. Civil Aviation Authority has created a lot of red tape for us. There's talks of trying to see if we can relax the rules for South Africa, at least for the researchers. And being an instructor for the drone syllabus and having to develop that curriculum as well. Yeah, it's a lot of expectations and sort of work we've got to do just to be able to fly a drone for 10 minutes. When I say a lot of work, you're looking at possibly like a couple of days of work that you need to prepare for a 10-minute flight. Is your the difference? This is the issue that we've seen with research. You look at, I've got a lot of space-related images over here, but a few years ago, a lot of billions of dollars was going in. I think it was NASA that was working on a pen that will be able to write in space. And I think it was the Russians that came like a few months later, and they were like, "Oh, don't worry about all that technology. We just use a pencil." And so the thing is a lot of time gets wasted on what is not needed. New stars being discovered, billions of dollars going into that. Yes, it's another star. It's going to make any difference to us. A new rocket is going to be launched. So, is it going to make any difference to our lives? There's some things that are making a difference. I'm not saying that there is research happening on the International Space Station that's not important. There is. But we need to start, find that thin line of what's important, which is a waste of money. ROS, the Robotic Operating System, or ROS2, that's been developed recently. It's made actually things so much easier. You've got able to control the robotic arm, maneuver it, simulate it, you're able to transfer it to the actual robot. You're able to do mapping of a robot. This was actually done I know that in 2015, this was sort of common tools to be used. I'm actually at the moment already busy marking dissertations and theses where a robot is being controlled using ROS to maneuver itself through a building, or not even a complex building, just a single floor, just within a passage. It's done already. So these tools are helpful for us to sort of bridge a gap, that we don't have to spend time on research that's just going to take time. we can use these tools, but it's almost like we're not using the tools, we're trying to redevelop them. So yeah, 3D printing, like I say, 3D printing is now something that we're all able to do. Just some examples of some of the things that we've 3D printed. Electrodes, using conductive filament. I 3D printed these electrodes, and actually had a medical doctor, an anesthetist. He went and used it, tested it on his patients while he was, they had operations happening and stuff. And he was like, yeah, and he's able to get good signals from that. Our touch hand, our prosthetic hand that we busy developing with. And I'll tell you a bit more about that as well. But, we're able to 3D print this now in the lab. We're able to do it in South Africa. And it just helps in terms of how we, pursuing things. So in case you don't know, we got the Sabathon 2024 happening in the end of October. That's a prosthetic Olympics. And we did it in 2020. With COVID, that was like all around the world type of thing. And the Swiss have now said, they're happy for us to host a hub in Durban, where we're going to have at least a task for the prosthetic arm. As in the referees and timekeepers and stuff to monitor everything's going okay. But it's a big task. Like Michelle was saying now as well, it's not always easy. Like there's this, technology being developed. Even the internet is not that easy. And the thing is we've been created in such a unique way that we cannot replicate a human hand. To do the same functionality, to do the same, ways of picking up things. Just look at a baby when it's born. Hand comes out, it's moving. There's no way that you can recreate that. And so, it's a challenge just to try and help people that have lost a limb. PCB boards being 3D printed. No etching required anymore. So, prints that we did actually last week at Nelson Mandela University. We're busy printing our electrodes as well as our circuit boards that we're going to be using for our prosthetic hand. 3D printed PCB boards, that's something that almost sounds like of the future. It's not something that we're able to do now. Electronics. Raspberry Pi board, Arduino board. Now as we just go and buy it, it's costing you, that'd be about 300 Rand or so. You're able to get any of these boards. It's got etching done, it's got the components soldered onto you, the holes are drilled. You just have to plug it in, program it. It makes life so much easier. So again, a lot of time is actually saved that we don't have to spend on building these things, and we can actually look at the more advanced type of software and artificial intelligence. So we've heard about GPT this morning, and you might not know this, and you can Google it if you want to check if I'm making the correct assumptions over here. But South Africa is top 7 in the world using ChatGPT. That is quite impressive for a small country in the bottom of the world that sort of, not doing much. I thought like other countries would be, your larger countries would be like on top. Yeah, we're using artificial intelligence. And the thing is like there's this thing of like, we shouldn't use artificial intelligence. I know of so many, if you're in the academic sector, everybody's like, you shouldn't use ChatGPT for research publications and to write up your literature survey and stuff. Why not? No, it's cheating. Okay, so tell me, what's the difference of you going to Google, typing in search for robotics, getting 100 pages over there that you're clicking on and that you're extracting information from that, and having ChatGPT doing it for you in 15 seconds? I mean, you've got to go back to those web pages and go and check if it's legitimate. Because, it's like spam phone calls that we're getting all the time. There's a lot of things on the internet you can't trust. We need to verify that. But we can get the information much quicker. It saves time. Machine learning algorithms. we've made a device a couple of years ago where we're able to, it's with Internet of Things, we have to monitor a patient's vitals. A person walking around down the street, we have to monitor their vitals. As soon as it detects stroke, heart disease, any issue, notifies the doctor immediately about it. We're able to compare those results with what the doctors would have done in their analysis. And it was like one-on-one similar sort of scenarios. Using machine learning algorithms. Our EMG electrodes to make the prosthetic hands work. We're able to, upload it onto a virtual system, onto a cloud, and it's able to generate for us with machine learning algorithms, able to learn the signals that's been generated from different people. And within a few seconds, we're able to have an algorithm that we're able to implement and we're able to use. Yeah. We're able to use these tools. It's just saving so much time. So, robotics research is causing us to think outside of the box. This is a man that we used in the 2020 Sabathon event. While that's just busy playing, show you sort of some of the things that we did and stuff. South Africa is in a unique position with research. We are able to think outside of the box. We're able to solve problems. Often it is that, and I think this is what I find sort of quite interesting with other countries. They've got the equipment, they've got the technology. No thanks, Michelle. I'm not saying your research is any bad also, but people overseas don't understand the issues we are having. They don't know what load shedding is, what inspections is. You tell them about it and say like, but why can't we just have quick online, chat, video call? No, because I don't have Wi-Fi. But what's the issue? Like, can't you just they don't understand that. So we've got all these difficulties, but from that we get experience. We're able to solve the problems. Okay, so let's look at the future. What robotics research are we going to be pursuing? Does it help people, or is it just theory? So many people are just doing theoretical research because they can produce publications. Oh, so stick that onto a robot. Oh no, we won't be able to do that. Was it those robot wars? Alan, is that what you say? What's the point of that? Robots killing each other. So much money just going down the drain. I mean, like robots are supposed to do tasks. This looks like some of our funny projects where robots got a hammer and a nail and it's just like destroying itself. Or transfer of an egg from one point to another point and then distraction. Go and put lipstick onto you. Why must a robot do that? Why can't you just, I don't know. I don't do the lipstick thing, but I'm assuming, and women might be able to confirm this. It's not that long task to do. It's quite a quick task, I think, from what I've seen. Washing your hair. Again, this looks like so much like a funny project. It's not going to work, why are we spending money and time on this type of research? So, Internet of Things, artificial intelligence. Yes, it's something that's been developed over the years. It is something that is actually happening, especially overseas. I mean, for example, I'm busy driving my car. I want my car to be able to tell me, oh, listen here, we're detecting that there's something wrong with this specific unit inside of your vehicle. It must be immediately making a call to the repair center. Say to me, listen here, there's something wrong with this car. It needs to be sorted out in the next, let's say, 500 kilometers. The repair center knows what part to go and order. It's not a thing like you first have to go to the repair center. It's going to take 2 days for them to order the part and whatever. They already have it when you get over there. There's so much that we can do in terms of Internet of Things. It's not being used really. People talk about the cloud and they actually think it's like a rain cloud that we are uploading things, not understanding it. But the thing is, though, is we've got this Internet of Things. There's tools that we can use to help people. I mean, this is using ChatGPT just to be able to place the objects correctly, to be able to do certain search algorithms, to find the microwave. We need a good coffee machine over here as well to this morning's early wake up call. But yeah, it's, we're able to use these tools. Why can't we use it? 3D printing has changed over the years. And I mean, the future is in terms of like bendable 3D printed parts. And this chair that's able to be flexible. Just looking at like fourth dimensional printing aspects. This business card is quite a nice example. I have my business card over there. It's got 4 different views over there. It's an infinity card. So you're able to keep on just turning it around, giving you different information. And okay, it's an expensive business card. At like cost prices is about 400 Rand business card. But these are things that we are able to start developing. We have over here materials that we're able to 3D print. It's able to, have got like memory alloys type of things, so put it back in position. What about printing things like ceramic? So we've got clay material coming out over there, printing these amazing pots. I think it's the African culture centers that we were at even last night. That would have been quite nice for them to be able to print that and have a display. Much quicker than what it took them to do it. But it's amazing techniques, patterns, and things we are able to do with it. It's different materials we need to explore. So in conclusion, I know that lunch is coming up and we've got still 2 presentations to happen. What is going to be the future of robotics in South Africa? How are we going to be pursuing this? Our suggestion is we need to look at open source. We need to share code. We need to share designs. We need to share ideas. Get your information out on publications if need be and stuff so we can, and make it available that we're able to sort of read it, hold on to it. Don't go into the intellectual property aspect of things and then, it takes like 2 years before you can actually publish anything because, you're trying to keep that information. I mean, Michelle's been busy doing research that's similar to mine. We could have been collaborating on this. Michelle's been publishing, but, we need to sort of interact and network with each other. I mean, I've got a colleague at CSIR, busy doing drone research, pretty much the same research we're doing over in my lab. Why are we duplicating the work? So we need to collaborate. We need the networking. How cool this sort of environment we're having at the moment? We need to prevent that there's not parallel research happening. Another example would be many years ago. I think it was probably about 10 plus years ago. Stephen would be able to remember more details about it. RoboCup robots we did. Each university or institution in South Africa was building a robotic soccer player, so to speak. It was a good initiative, it was like, but each institution's robot had some aspect that was good. One was maybe the mechanical design, one had maybe good electronics, one had maybe some good local artificial intelligence, another one had global artificial intelligence. We were working together, but we were doing our own thing. So, if we brought everything together and we're actually working together on different aspects, because let's be honest, each research group over here has got some strengths and some weaknesses. And so we're able to share that, bring things together, make it work. It's multidisciplinary. We need to expand our horizons. We need to solve problems. We're engineers, aren't we? Oh, no, but you can't do any research outside of robotics. Why not? Aren't you supposed to be solving problems? Give an example over here. We did skid tests on a gravel road with different cars to be able to identify how vehicles were maneuvering as soon as you have ABS brakes or ABS brakes was disconnected, different tire conditions. And, you do those tests. You have to say, these are improvements that need to be happening on a car. That's robotics that's going to happen to make those improvements happen, to control those vehicles to be more stable. Why can't we do that? I mean, like I was telling to you, or like I was saying that mechatronics and robotics got mechanical aspects, electronic software. And so often you've got to look at drones, or I know even rockets have to have like mechanical structures that are strong. So we started, well, I did some ballistic tests a couple of years ago. It was like, oh, Kevlar, you just make your thing out of Kevlar and it would be like bulletproof. I'm a bit worried about the people wearing those vests, so I'm not saying that they are effective, but we did tests with different caliber. Oh, no, small bullets, don't worry about that. That won't be able to do much harm. They were actually the most harmful of all the tests we did. So the thing is that, we're testing the Kevlar. How well is it working? Is it, how many layers are you going to need to be able to have some form of protection? So again, it's a mechanical aspect, it's ballistics, it's not robotics, but why can't we research it? We need to do this to be able to solve the problems that's going to be used for our drones, for our different robots we're going to have that might need to go into fires, might need to go into mines. That's what's needed, is that Kevlar research. Okay, so I'm ending off with this. You'll see that over here, there are like different social media platforms we've been looking at for the lab. It's a smart lab, and then we discovered there's already a smart lab. So we're obviously smarter, a smarter lab. These are like all the links and things where you'll see what's happening. We'll also be posting on a lot of things for the Sabathon week coming up. That's from the 21st of October, we're going to be setting up, and then we're going to have the actual event on the 26th of October. It'll be live streamed as well across the world. We will also have on YouTube the video segments of the different tests we've done and stuff to give you an idea of what's happening. Also posted updates on the DutchProsthetics.com website. There's all these different social media things. But again, it's like these social media things we've got out there, and it's supposed to bring us closer. We're supposed to be able to link up with each other. LinkedIn is also great, but I'll be honest with you, it all depends on who you are. But if you've got 1,000+ connections, and after like scrolling for 5 minutes, it's like Facebook, it's showing you things that you're not really interested in, and then you're like, okay, close the app, and then you continue with work. There is things happening among us. There is, and we need to maybe have a more closer network way that we can collaborate with things. But again, I do thank the organizers for this event. It's really great, and I do think we really do need to do this more often, at least once a year. Hopefully, if ICRA is willing to make that available, it will be a miracle. But it would be quite nice to see that happening. Okay, thank you very much, everybody.
Can I take 1 or 2 questions from the floor?
Just important, so.
See, there are people looking forward to lunch. But we have 2 more presentations from your students coming up now. So
ask them the questions.
We'll go right into that. I think the first presentation from Siposetu. Thank you. Let's put our hands together once more for
I don't know.
graduating fellows. Hope you're good. My name is Siposetu Alowosekhuluvayo. I was born in KZN in a village called Dwedwe. It's a rural village. So, growing up as a kid, each time I visit the nearest town, which was Tongat. Some of you may be familiar with Tongat. It's in the north coast of Devon. Each time I visit the town, with my mom, I would see either a person on a walking stick or a person holding their arm like this, signaling a disability or an inability to complete or to do normal tasks like everybody. So as a kid, I would find myself in a space where I think about how each of the circumstances that these people are facing could be addressed. So when fast forward to 2023, I had a casual conversation with Prof. And we happened to talk about the research that research topics that Prof has. And this happened to be one of the topics that Prof presented. So that's how I happened to be part of this group. So the title of my research is Design and Analysis of a low-cost mechatronics prosthetic hand. So, like I said, I'm from KZN. I went to University of KwaZulu-Natal, and I'm from Smart Lab. So, basically, that is what my research is about. And I've almost forgot that which is my presentation here is part of what I submitted on last year and also what has been done after I submitted. So to give you a little bit of a background to the approaches or different approaches that are taken by designers and researchers of the prosthetic devices, in particular prosthetic hands. There's two of them. One of them is to try and mimic the real hand. The other one is to try and simplify the designs and be specific in terms of wanting to achieve activities of daily living. And that is, each of those have their disadvantages, pros and cons. So the one that we took is a simpler one as the target. If the product were to be commercialized one day, the target group will be impoverished communities from my community and around Africa as well, and other communities around the globe. So I present to you Touch and 6. So Touch and 6 in the sense that there have been researches going on before I came, and I happen to be part of Touch and 6. So as you can see, this does not look like your hand, right? So because of the approach that we took, we're simplifying the physique, the natural look of the hand to try and minimize costs, bulkiness, and others. So as you can see here, the major components here, we've actually got two fingers. One, which is your index finger, and we've got what I call ring pinky finger. And then I've got the thumb. So the ring pinky finger, which is this one, this actually represents your 3 fingers. That's the approach I took in terms of trying to simplify my design. So fast forward to the modernity or the modern approach of that are used now in terms of like controlling the device. So what we have got presently is this method of controlling the prosthetic hand, which is mirror electric prosthetic hand control. It uses mirror electric sensors, as you can see there, which interprets the movement of your muscles and convert that physical motion into electrical signals, which are interpreted by the microcontroller board that sends information to the motors to control the fingers. Another control method is this one, which uses physical movement of the body of the amputee to open or close the hand. So this is our approach. We're going to use electric prosthetic control. So this happened to be the problem statement. High-tech prosthetics are inaccessible due to high cost. And from my research, I found that in South Africa, if you look at the commercial hands, most of them are in the regions of 100,000 rand. So that's quite a lot of money for someone who comes from an impoverished community to afford that. So also there's frequent replacements that are needed. For example, kids are actually growing up and they outgrow the prosthesis. And then therefore there's a need for a light weight and then a simpler solution. Okay, this happens to be my research objectives. What I need you to highlight here is the fact that number one, we wanted to design specifically for the competition. But more than that, we wanted to stay within the constraints of weight, costs, and then bulk and simplicity in terms of actuation. And then this is the mechanical design approach that we followed. We had two concepts. One concept was a purely mechanical concept. The second one was a mechatronic, which uses what I've presented above as the mirror electric control. So from a mechanical design perspective, this is the design design that we settled to after several field tests that we did at the lab. So the control philosophy is actually based on the mirror electric control. So what you see here is a power bank, which powers the servo motors inside, and another power bank which powers the nanoboard and the push button and those LEDs. So my electronic circuit is here, and these are the power banks. So when it came to testing, we had to produce like 3 forms of hand movements. For example, this one is pointing it's pointing a finger. You can see the index finger is pointed, and that one is like the ring pinky finger is closed. And then on that little picture, you've got the hand closed, and you can see the ring pinky finger is closed, and index finger is also closed. And then also on that one, you can see the index finger is open, and the ring pinky finger is open. So here I've got the video of the few tests that we did at the lab. What I want you to notice here is that since we have got 2 fingers, we've also got 2 electrodes. In fact, like two sensors. So one sensor is for the index finger, and the other sensor is for the ring pinky finger. So as he closes, as he closes, one of the LEDs are supposed to light up. Move to this one. Clean shot, that one. Okay. So here it will be clear here. Yes. The middle one, as you close the ring pinky finger, it's actually 3 LEDs. It may not be as accurate as I'm going to explain to you, but it's supposed to be like that. One of the LEDs will light up when the finger is pointing, just one index finger pointing. And the other one will light up when the finger is in extension. And the other LED will light up when the finger is in flexion. Also, again, I want you to notice here that these electrodes are targeting this muscle which attaches that finger, the tendon which attaches to the index finger. And it's also at the bottom, there is another electrode which is placed here. And as you move these fingers, the muscle is actually moving here. So these were a few tests that we did in preparation for the Subathlon competition that will be happening on next month, the 25th to the 27th, as Prof mentioned. This is my last slide, and I will thank my supervisor for the opportunity and the company in Durban that sponsored this research. And on that note, I will welcome questions.
Okay. Yeah. Any questions from?
With this type of control weights monitoring the muscles, does that work just as well with, for instance, amputees? Like, does that muscle still have the same measurements?
This is quite good. It's something called phantom pain. When someone is amputated, they can still feel some pain. What does that mean? It means that as much as the end is amputated, well, that part is gone, but the remaining stump can actually send signals via the CNS to the brain. So the answer is yes to the question. Thank you.
Another question.
I was going to ask, how long did it, in terms of mapping your gestures to the hand, was it 1-to-1 or you had to do an ML?
Sorry?
Mapping the gestures to the hand, the gestures you were doing. Was it 1-to-1 or you had to go through a machine learning process to be?
It was 1-to-1.
Just a quick question, kind of just following up on that quickly. What is kind of like the biggest bottleneck time-wise in this process? Because like I saw there was some delay, right, between when you kind of like, let's say, extend your hand and the robot, the prosthetic arm extending also. There was like quite a significant delay. Yeah.
Time to open.
Yeah. So like, what is the biggest bottleneck that is causing that?
The question?
So like, what is the biggest bottleneck that is causing the time? Yeah, like the biggest component of your process in terms of time, in terms of runtime, that is causing the delay between gesture and prosthetic arm moving.
Response time.
Must be the time to open, right?
Yeah, they respond after the
What
Yeah.
is the component that limits that?
Yeah, that kind of like has the biggest effect on that time.
Well, that can be programmed on the Arduino. You can set it to any time.
So that delay was like on purpose.
Yes.
Okay. So like you could have like real time, like when the person is making the gesture, your prosthetic also like moves 1-to-1 in real time.
Yes. As we were doing the tests, as we did the test, we kept changing the closing and opening time. on the code, on the Arduino code. So it's like a standard term, of course, but it can be changed.
Okay.
Apologies, I don't want to keep people from lunch. But thank you very much, Roseto, for that presentation. And as you can see, there's a lot of discussion. Please let's continue this over lunch and over the rest of the day. Our next presentation is Nkosi Gifile from KZN.
Greetings, everyone. My name is Nkosi Gifile. I'm currently doing my master's with Prof. So a quick backstory about me is that I did my undergrad in mechanical engineering, and I wanted to understand electronics. So Prof offered me a good project of where he wanted like a hybrid UAV which can vertically take off and transition into a horizontal mode and then go long operations. Yeah, so I was very interested in that project and then started exploring it. So in reduction for everyone to be on the same frequency is that UAVs, unmanned aerial vehicles, are commonly known as drones or aerial systems, as the name suggests, unmanned, meaning absence of a pilot on board, is a popular field that has been explored for decades in robotics. UKZN has contributed in the field with the duo Fumigam, which is contributed in 2016, and the S-Lipper, which was made in 2020, along with the Critical. Sorry, I butchered that name, I know. And then it basically, one of the design specification that was brought up is that the UAV had to contra-rotate. It had to use like contra-rotating propellers. So I explored that project and found that like Ingenuity, like a famous NASA UAV, which is currently working with Perseverance on Mars to identify, to explore Mars, is basically using the same propulsion system. So that was pretty interesting. It showed like advanced application of such research. So continue on that, we saw a gap in literature. I explored the literature, correct me if I'm wrong, but no one in South Africa was exploring these UAVs. No one in South Africa was talking about ducted contra-rotating UAVs simply because of the quadcopters and the fixed-wing UAVs. So quadcopters offer great stability because of their rotors, quad meaning 4 rotors. And fixed-wing UAVs are standard because they evolved from like airplanes. So everyone is familiar with that. And so we understood that and we did what we understood because, yeah, but what we wanted to do was a bit difficult. So we wanted to take like a company called Shield AI in America, previously known as Martin UAV, is developing this, but for single copters. Basically, this UAV has the ability to vertically take off and then transition into horizontal mode and then go. So I wanted to finish my master's in 1 year, and, and that was not possible. And the budget for the project was 10,000, and yeah, that was just not possible. So what we changed was the approach to this. We sort of like broke down the problem and made it into what a company called the Clio Donuts is doing, basically focusing on this part, but with contra-rotating with 2 rotors instead of 1. So I developed that. We narrowed the scope of the project, researched the hardware and software required to do that, designed and manufactured a flyable prototype, and then what I'm doing now, currently demonstrating its capabilities and limitations. So a quick design methodology which was used in this research was that it was used in parallel and integrated at the implementation phase. So I explored the electronic design, selected the components that would be functional for such UAV, and then focused on the mechanical design, generated various concepts from existing research. Due to most of this work is currently being developed in China, but here in South Africa it's not being done. But a thing to note there is that most of this work is simulation based and not a lot of like experimental purposes. And for experimental purposes, it usually in a wind tunnel with fancy equipment, very high cost, and we just didn't have the money for that. So all the facilities to conduct such things. So and then the software design, I did my undergrad in mechanical engineering. The basic code that I know is I did in second year for CH, so I'm not a good programmer. So my supervisor advised me to go with mission planner. So it was a bit straightforward, easy for anyone to comprehend. If you're looking to get into UAVs, go with that. So program mandatory setup, and then we implemented, fused the different electronics, mechanical, and the software, making up what? A mechatronic system. And then for the final design, we would have to think about the concepts that we have and then create a circuit for that. Think about the mechanical airframe that we have, create and fabricate a mechanical design for that, and then assign the proper parameters, because the software part of this mechatronics design comes in a form of firmware. A firmware is basically a software, but broken down a bit. So what you are doing in this UAV phase, you basically be changing multiple parameters. I was basically changing multiple PAD parameters to actually get this thing to work and to understand it. And I'll go a bit more on that later. And then we evaluated and then we were going to evaluate the performance of the UAV. And if it was not flyable or we saw some issues in it, we would modify it and then start the process again until we reach this phase, the final prototype phase. We still haven't reached that phase. And then the design work. This is a simple layout of the prototype that we work with, inspired by research in China. But the difference between that research and this research is that they used like a support structure up above this to make their component basically top heavy, not bottom heavy. So it's a bit of a mouthful, but yeah, it helps with stability purposes. So we weren't focusing on that. We just wanted to understand the fundamentals of this project, this system, and then build on that. So this is the component we have. We have a duct which offers lift and protects the propellers. We have propellers, brushless motors, and flight controller, which is basically the brain of the UAV. The PIC sockets commercially available, and LiPo batteries to power the UAV. Yes, so the material selection that was used was also considering that the cost of the project. So basically, we went with plywood instead of like carbon fiber, which is more strong and lightweight. But we went with plywood, and then we went with for manufacturing the duct. We went with 3D printing, which was a solution that was available in house. And then we ran some simulation thanks through the help of a VECWEST student which ran the simulation, because I did not have the time to do that. He ran I gave him the conditions, and then he ran the solution, and these are the results, basically exploring if the UAV will be able to house these motors, and provided that the thrust that is going to be generated, would it be able to be supported by these stators, and to justify why we used a thin duct instead of an airfoil duct that some people might opt for. But it came down to the manufacturing costs and the printing capabilities and the complexity. So that was justified. And then the electronic and software integration is basically inspired by Mission Planner. You're welcome to go through AduPilot's website and see how to run a PICSOC with the drone, exploring quadcopters. Quadcopters are nice. And then the manufacturing phase. This is the fourth design, not the final design, but the fourth design. It was the only picture that I found for this presentation. And a quick video of the test that we did. Okay, this was the beginning stages for this research. Crazy things are happening. Crazy things are happening. And we tried the safety approach on opting for, it was either doing this on MATLAB or tying it down and actually seeing the parameters. And I opt for this because I like my hands and we didn't have the computational time. And then spoiler alert, this is the first stable flights that we had inside the lab. So it took a lot of like playing with PID controls, and yeah, that was nice. But there was still a problem to this UAV. Like as you saw, okay, I'll elaborate on that later. Another issue that we saw about this UAV is that it started to spin. The spin, this loss in yaw, okay, basic pitch, roll, yaw. Those three things: pitch, you pitch forward, pitch back; roll, you roll right, roll left, and then yaw, actually spinning like this, spinning to the right. So that's like quick navigation of UAVs. So we saw that's a problem. There was no yaw inputs there, but it's okay. So we wanted to mitigate that. And we saw that there was actually a hardware problem due to the low cost of this project. Like we're using batteries that are below minimum requirement for the system, so the system would overshoot. And then thanks to the potential of this project being seen, our supervisor was able to procure some funds, and we were able to continue with the research. Installing, we made basically a 4S battery that was capable enough to do some nice things and overcome the overshooting problems, as well as like increase the vanes or the control surfaces for the UAV. So these were the filters that I did like on the 15th of September, 15th or 16th of September this month. And then we are basically testing the takeoff. Something broke on the landing because it was going very high. And then something interesting to note is that the maximum height that was recorded was 9 meters. So 9 meters is basically 2 times what you would see from headlines, you know, like wires. Head wires, sorry. So, or a 3-story house. And then these were the hovering tests. It was very harsh. So what I noticed was during this testing phase, when I went with the wind, the helicopter would try to counter it. And then, yeah, I'm still analyzing the flight logs from this test. So yeah, I might not be too clear about that, but the performance was promising, and there's a lot of potential to this. And note this, the only flight modes that were used here was basically stabilize mode and altitude hold mode. So stabilize mode helps with the vertical takeoff, like it helps like the UAV to balance whilst it's take off, like be stable. Whilst altitude hold helps with the hovering, maintaining a certain altitude. And then there's this third mode that I'm looking to explore, but with time I will explore it. It's auto tune mode, where the UAV actually talks to itself using its algorithm, saying, "This is me. I'm in the air, and I'm now understanding my parameters." And then with that, the UAV can actually fly pretty well and actually compete with like a drone night. So this idea is pretty cool, and I hope I'm gonna pursue that. So current and future work, we're looking to get a publication out of this. I'm looking to finish my dissertation. Yeah, next week, right? October is pretty wild. But yeah, we're doing that, and yeah. The call for action, gonna skip the slide. My supervisor talked more about it. Like everyone was talking about it. We need collaboration. Please do reach out. I'm gonna be reaching out to Dr. Fisher. Please do not deny me. I like your research and I hope to work with you in the future. So, the end. Any questions?
Any questions from the floor?
Just a quick one. What's the advantage over a quadcopter? Like, why would you do this rather than a quadcopter?
It's basically one rotor is better than two. Two rotors is better than four. So basically, if you get a good system with two rotors, it's better than four rotors. So yeah, we're going with that approach. And if you notice the current trend in the UAVs, we're going for hybrid approach, or people are developing like energy sources, better energy sources. Hence, that's why like there's an introduction of like fuel cells to actually power UAV and actually increase the time needed to operate such UAVs. So it's either you're going with the mechanical part when you're trying to improve this and make it hybrid so that it can run for longer durations, or you might go for like alternative powering sources. I hope I answered you.
Yeah, no, that makes sense.
I have another question.
Yeah, it's okay.
Okay. Let's put our hand again. Further ado, we can go for lunch.
CSR has strategic objectives. First one is conduct research and development of formative technologies to accelerate their diffusion. I think that's what most people know. CSR is they do research, right? It's the next few ones that you're probably not familiar with, right? So improve competitive of high impact industries. Okay, we must work with industry and support them. Drive socioeconomic transformation through our area that support the development of a capable state. We must work with other SOEs, improve government, right? And this branch for our centre, we must work with 5 different SOEs throughout the year. Okay. So SOE, another state-owned entity comes to us, we must support them. Okay. The next one down is human capital development. We must transform our own capabilities. So that is make sure people are studying, bettering themselves. And most of that is linked to top 1 research. Okay. Bottom one, diversify income, attain financial stability and good governance. CSR is only sponsored by the government for 15% of their budget. The rest of it must be found outside. So we go and get industrial projects, work with industry. Even if the state-owned entities are going to pay us, we then get income through there. So we have a small budget from the government. It's called the parliamentary grant that we use for core research, but it's very directed research. It has to have an industrial partner that we can play with. Okay, so our research is very governed by these strategic objectives. Okay. We have a lot of partners that we deal with. Some of them are known to you, some of them are a bit more obscure, but this is not a comprehensive list. Okay. Again, we try to work with as many external partners at the as possible, because that's part of the mandate. Okay, we can't sit in our little cocoon and just work. Okay, so when the CSR went through its latest round of restructuring, we ended up with 9 clusters, right? And they're broken up into different divisions. So you got the advanced agri and food, future production chemicals, and next-gen health. That's 1 block. I'm in future production manufacturing. That's also linked to mining and defense and security. So we're in another block. Okay. Then you've got smart places, smart mobility, and next-gen enterprises. So we tend to work within this area. Work a lot with the mining people, work a lot with defense. That doesn't restrict us from working across, but our main partners that we work with are in mining and defense. Okay. So a little bit more down, I'm almost finished into the background stuff. In manufacturing, we have 4 main entities. We've got 2 impact areas, 2 centers. Impact areas are completely outward facing. They've got external clients. They have very little parliamentary money. They must get their money from outside. And that is advanced material engineering and industrial sensors. 2 centers, they do receive a bit more parliamentary money. They could do a bit more blue skies research. And so we have the Center for Robotics and Future Production, and we've got the National Laser Photonics Center. So the center, each area must have objectives that they're trying to achieve, and ours is to enable manufacturing industries to be globally competitive through. And then we've got a couple of points there. and it's all around 4R, right? Being able to improve industry and make them more relevant and competitive. Okay. So what does the center look like? We've got 3 research groups. You can call them focus areas. First one is future production systems. They look at how do you make a company more competitive? How do you make them embrace 4-hour technologies better? They also deal with digital twins, a lot more automation, and the learning factory and smart factory also fall within their purview. I head up industrial AI. You're looking at how do you make decision support structures. I also deal with the higher level stuff for mobile robotics. Industrial robotics, they're more our mechatronics group. They build things, right? Low level coding as well, but they are there to make sure that if we need something built, it's done. So a lot of mechatronics engineers, mechanical engineers, electronics, software side is more low level. High level assists with our group. Future production systems uses both of us to make sure that plants and the industry moves forward. Okay, so that's how we are interlinked within our center. So we have 2 core platforms, the Learning Factory. So Learning Factory is set up so that 4-hour technologies can be, that you can train people in 4-hour technologies without having to go to a university and things like that. Short courses. Okay. We've got a team that's dedicated to dealing with that. Okay. And the Master Learning Factory is actually within the CSR. So they do tours and things like that. And you can go through, it's meant for, we don't normally take schools through it. It's meant for adults, improving adults and showing technologies, even to CEO levels. We've had, Graduate School of Business sends their people through it as well, so they can be exposed to technology. Okay. If the CEO doesn't understand the technology, he won't implement it. So if he wants a quick view on what is the different current technologies, they come through, it's a 2-day course or whatever, and they get an exposure to it. This group also looks at how to deploy learning factories. So Anglo wants a learning factory. We're busy with that at the moment. The motor car industry in the Eastern Cape wants a learning factory. There's one more one that they are looking at. They're closing their plant down, but they don't want to leave their staff in the lurch. So they're going to upskill their staff and then close the plant down. Okay, I think it was one of the mines. Smart Factory looks at how to process the digital twins, how to make something that's sitting in the 60s, because you know how many South African plants are actually sitting in the 60s. Very manual, very paper-based systems to move them forward into the 20th century, right? This also deals with change management. So how do you take your company through it? This is the more interesting side of things, I find. I don't really do much of the plant stuff. I like playing in this area. So product development, product localization, product digitization, so adding value to how you produce your systems. That's one group that's also very closely linked to future production systems. And then we've got our robotics area, right? So we do build customized robotics platforms. In there, QC, QA, inspection, automation, condition monitoring, all of that falls within this area. Okay. So we are a business, right? We have our offerings, and I'm not going to go in detail of this. And we have our business model, how we map our platforms and to our business model. Okay, so we have to report on finances every 2 weeks, right? So we run like a business. Okay, so when I've spoken to a lot of people, they thought CSR just makes money, they do research. We're a business. Okay, so I've spoken a bit about the learning factory. So we have something called the intelligent integrated work cell. So that includes things like manufacturing execution system that's keeping track of everything that's running through your plant. How do you know when this guy's finished his job? Let us move on. How do you keep track of quality control? We build our own system as well for low cost applications. Again, South African companies, smaller ones, SMEs, mainly have paper-based and Excel systems. How do you try and get them to be a bit more automated? In that in the work cell, we've got part of the robotic system. So we've got ABB, we've got cobots, quality control. So the whole system acts like a miniature factory. So that we can demonstrate when people come through. Okay. There's a picture of our lab, actually. Benji, it has changed a bit since. Okay. I did want to include this, right? When COVID hit, there was this, Ian spoke about it, everybody's building ventilators. We were also part of those like teams, but we did manage to produce 18,000 units in 6 months. From start, design, set up a manufacturing system, quality control, approval, out to hospitals. Okay, so CSR does adapt when needed. Slow, but it does adapt. Okay. But this was a good success story for us, right? Being able to get that out the door, and we've got affidavits from people that were on them and that were saved and stuff saying this really did work. Okay, so now let's get to the fun stuff, robotics. So our focus is industrial robotics. Okay, we do some research, I'll show you that, but most of it is industry facing. So Transnet came to us and said, okay, we have some of these problems. Missing of stolen tracks, literally. I mean, that's a train, there was tracks there. Okay, that's a problem. Something going onto the tracks, or you've got tracks that have been like washed away. How do you deal with this? So we developed this guy, a survey inspection device. Okay, there's a wire that's called that. It's our friend Sid. So Sid was designed to run ahead of the train. It's a fully autonomous system. It does communicate back to the train, and it reports on the status of the track. Anybody know why you would want to be about 2 kilometers in front of that train?
Stop.
To stop the train. But the train is the only vehicle that can stop in its own lane. You won't do that with your car. Right, so Sid would run ahead, report back to the train, and do inspection on that track. Originally, it was just for obstacle detection. That was the biggest problem they had. But then we started looking at all the other little side problems. So if you look here, it had its own thermal camera. We track people. We track the track itself to see that it is there. Okay, check for people, make sure that they are in a zone that was okay. And we did map the area around. So every time we went past it, you would know, is there stuff there? Then they wanted us to do a bit more inspection on the track. So we did corrosion and then swirling. So swirling is when it actually blows up little pieces of metal. And then the profile. So that a laser that looked at the profile of the track, and you could actually watch the wear of that track before you would have to. So the last version of it had a multispectral camera that would look at the overhead line. CSR did develop the technology to look at corona. So if you've got a faulty insulator, there would be a corona discharge. You can't see it with visual eye, and you could have a corona cam, and you could see that that insulator was damaged. Okay, so you could do a full inspection. I didn't mention clips. You could see if there were clips missing. You could do a full inspection of the track as you ran down in front of it. Okay, so this was quite a good all-around project. Had a lot of good aspects that we could implement, and that it grew over time. Then they turned around and said they don't have money for it, so we stopped. Okay. Along with the train, if you wanted to know what's happening on the track, you should actually know what's happening on the train. So we built a vehicle conditioning monitoring system for them as well. This one they did buy. We did a batch of 15 first, and then we did 30 after that. So it's literally a black box for a train. So every bit of information that you could capture from a train would go into this, and then you could. It also had its own satellite link and everything. So these are deployed on whatever running stock is actually currently running. Okay. National Technology, NITSA, they look at standards for measuring standards for South Africa, right? They are the place to go if you need to be calibrated for measuring. They would very manually measuring their gauge blocks. So if you've got a pair of calipers in your workshop or whatever your production line, you've got a set of gauge blocks, then you would take your calipers, measure against a gauge block, and you would see, okay, my calipers are still good. But you have to send those gauge blocks every now and again to get checked. Okay. So they wanted to automate that process, so we built a Cartesian coordinate robot, pick up the block, put it in, get measured, put it back in the box, and then produce a report. So they've got now 3 of our units there with them. Okay, so automating their systems. Sorry. We're doing, this project is currently running at the moment. This is the Delta robot. They want to use a Delta robot to measure different objects, right? Now, standard Delta robot with all the play in that is not going to give you the accuracy that you need. So this was their first version of it. It had very accurate linear measurement units that would move around with it. But they wanted to go to a laser-based system. So I have a laser from the top pointing down at the target, but the tracking of the laser was done by the Delta robot. So we are busy with this at the moment. So we can do the whole process. So we start with the design, and we use multi-objective optimization. So genetic algorithms to produce Pareto fronts, and we can optimize the design for their parameters. This was all modeled, and now we're in the CAD phase, and now we're actually being in manufacturing. So this is the kind of more industrial type of robotics that we do. Okay. Righty Pharmacy. Okay, Ava machine. So these little dispensement packages, I don't know if you've ever gotten medicine in that. Okay. There is no system currently that can pick up those and dispense them, right? They normally dispense them in like a full bottle. So this Right ePharmacy, they came to us and said, we want a machine that could take packages like this and then be able to dispense them to their clients. Right. So this machine, this is just the back of it. Open it up. You see it picks up a tray and it dispenses it. But you'll see it'll get to a point where it's into the scan. It's a separate scan over here. This is a demo model. So what it was doing is, if you go along, you have a bag, so that every one of these little lockers, and they have a much bigger locker system. We only built the smaller end. Would have a particular kind of medication. You would go there, the panel in the front, you would show them the card. The card would say you would need this medicine, this medicine, this medicine. It would then go to the tray, collect it. But it's only labeled on the one side. So the head has the scanner as it comes along, scans it, grabs it, puts it down. But if it goes there and there is not, the label's the wrong way around, let's say they put it the wrong way, they would go along and then show it to that scanner and see if that is the right medication for the person. And then if it is, then it goes and gives it to them. If it finds an incorrect medication in a bin, then it would reject it. Okay, so this then was deployed at one of their facilities to try and speed up the treatment of medication, just your chronic medication and things like that. Oh, sorry. Go back. Okay. Does anybody recognize this? This is a testing machine to test your road. Right? The CSR built this thing quite a long time ago. Then it was licensed to Dynatest, American company. They build them now. So CSR built it. They did all the development work. Then this was shifted over to, the technology was sent and went to America, and they pay us fees, right, for using it. You can literally test a road to destruction with this thing, right? It's a big piece of equipment. I mean, there's a person in the machine. This one was for, we do work on it every now and again when they want to do upgrades and stuff. This one is for the American Air Force, right? They wanted to see how their wheels were interacting, the VTOL aircraft were interacting with the runways. So as the aircraft went down, how does that tire interact? So this machine was built for that. Why is it skipping so fast? So inside, yeah, you can see that the tracks. I didn't get a video of it. That was one thing I didn't get. But this skirt on the side can raise or lower, and it's completely temperature controlled. So they can increase the road temperature or make it sub-zero kind of thing. It really is quite a large air conditioning system they can sit in there. And then this is the actual platform that can hammer that tire into the ground, depending on how fast that aircraft is descending. So they can do a straight descent, or they can do an angle descent with this system as well. Okay. More classical robotics. Okay. So we've done quite a lot of work in 3D map generation, 2D exploration, multi-robot collaboration. We're getting back into this now, multi-robot collaboration. So this video is of our lab. The robot was just dumped in there and told, explore until there's nothing to explore, right? It would run around, path plan around the obstacles within the lab, and then produce the map of the area. This will pull out the back end. And then realize, okay, I have a hole in my map over here, like that. It's got the arrow, and then it will repath plan to redo that. Okay, so This was a project that was funded by the government. This was part of the parliamentary grant. We said we're going to do so much on ground-based robotics, and this is one of the projects that we did. But effectively, we create little toolboxes, and then when we need them, we just pull them in for a project. Okay. This vineyard inspection, so outdoor robots. We have done a fair amount of outdoor robots and mining robots. I'm just going to include this one. This was quite a fun one. This is a joint project between CSR and University of Stellenbosch. And they wanted to be able to have a system that can drive up and down inside the vineyards, map the vineyards, and look at a whole lot of parameters for that vineyard. So crop density, state of the fruit, soil monitoring. There's quite a long list of stuff that they really want. The other group leader. Okay, so I did include that version that you saw was version 2. This is Gen 3 that's currently running around. It's a much bigger platform. They wanted to put more and more sensors and run for longer, so we built them a bit more as well. Okay, so some of the stuff that we did was canopy density, and there was a dashboard that would segment out each vineyard, and you could then click on that and you can get the history of that particular plant. Okay. Something a bit more current. This is currently last year, beginning of last year, 2 security companies in Oman approached us for a robotic platform that could do patrols at night. They just want to be able to do walking speed around their properties, and they want to look for people and vehicles. So we have put together a platform. This was ready, prototype, rough and ready kind of thing. We just wanted to get the proof of concept right. Oopsie, went too far again. Okay, yeah, it'll play. Okay, so they didn't want an overcomplicated dashboard. They wanted just to be able to do waypoints around an area. So you would just click on the waypoints. The system that would then be initiated, it would drive. Okay, this is sped up a bit. But every time it spotted something, it would log it in a database, and you can go into the database and actually have a look. So here it is, front cam, right cam, and then 4 cameras on the top to be able to just like look around and look for things. So running around, and then like if it found somebody, like there's myself and a colleague, it would pick them up, but it would also log them on the dashboard. And you could go in and see, okay, what triggered this event. Okay, so they wanted a platform that could just walk at walking pace, right? That's all they wanted, right? So this was first version. We are building its bigger brother. 4th client came along and said, we like that, but we wanted to go faster. They wanted to get up to 40 k's an hour. So this guy is a lot faster and a lot more computational power, because the faster you go, the more you got to process, right? So it's this CAD rendering. It's in the workshop at the moment getting built. Okay, so we are doing, so these are for security type applications, because again, we're in that band of mining, security, that kind of thing. So the mines want it, security companies want it, something. And it's not to take away jobs, it's just that they don't want to have people walking around at night, right? It's the big thing about how do you keep your people safe. Okay. We did present this to the Department of Defense, and they are also interested in getting some kind of system for doing patrol work as well. Okay. So, CSR does try to get money for researchers, right? We try to get programs going, but the DSI has their own agendas, right? So we did get a small amount of money for a robotics program, robotics and AI. Currently we have 3 partners. We have requested additional money for more partners, right? They already said, why don't we have more partners? I said, give me more money. Okay, so Stellenbosch, UCT, and Pretoria University are the starting points, okay? And the focus is in ground-based robotic systems, preferably on the AI side of things, okay? So, this is like the very high-level framework for the thing. Is functional is the basic control of robotic systems, okay? If you're starting out your research group, particularly like we're starting in University of Pretoria, you always start in the functional area, right? Can you control your robot, right? Then you go on to behavioral, so that's your mapping, SLAM, all that. But we're trying to move everybody up into the cognitive side of things, a higher level AI that's needed for robotics. Okay. To make sure that everybody's on the same field, the ESI gave us money to design a robotic platform. So each of the 3 universities got their own Voyager, right? Fully equipped, all the sensors, everything, so that we're on the starting point. They can add to that robot. It does have this top platform and a network point and power and everything. So they can add their own sensors, but they've got a platform to start with. So they've got a platform. We've also got a platform, so we can collaborate with them as well. Yeah. Basic breakdown of the system, right? Completely localized. So I mean, we can produce these if we need more of them. And with the gazebo model as well, because we do believe simulate before you deploy, right? Okay. It's meant primarily indoor. We have tested it outdoor. This was running around our campus. I mean, so this is our building over here, building 17, drove around, drugs of knowledge common, mapped it nicely and things like that. So if you've got a fairly well-maintained lawn, you'll be fine. Okay. Okay. DSI wanted to see Parliament, so we took it down to Parliament. Still a UCT's robot, and it went to Parliament for the opening of Parliament this year. So hopefully this will attract more funding for robotics research. Try to do our selling job as well. Okay. In robotics, we've got a small group that does UAV work, okay? The main focus is GPS remote areas, right? Indoor flight or in mines and things like that. We're trying to avoid the outdoor flight because of all the red tape associated with it. But it has its own challenges, right? To be able to deal with a closed environment. We started out with this big guy. We bought the DJI 600, but our focus is not the UAV, it's more the sensor payload and the processing of the data. So there's our lab. We did a flight through it and mapped that lab. Okay. This way, it was hair raising trying to get that to work, because that is a fairly large UAV for that area. Okay. Security cam. This is an MSc project. Again, our staff, if they don't have an MSc, at some time you're going to be told you're doing an MSc. Right? Okay. And then if you want to progress, you'll be told to do a PhD. So this was a project for if you want to deploy in an area where you don't have surveillance and you suddenly need surveillance. It could be something as simple as a concert, or it could be you got a riot going on. This was deployed, so you just literally trip the robot at the bottom of the pole, and up it goes, and you've got a mobile surveillance system sitting on the pole. Okay. Department of Defense liked this one as well. They wanted us to build more of that. Okay. They had a fairly good camera on it, things like that. You could pan, talk around, the normal like security camera stuff. Okay. So that's the main like robotic stuff that we've done recently. But again, we're not just doing robotics there. We have to be able to deal with industry. So We've done a lot of visual twinning. So how do you take your factory layout, optimize it, that kind of thing. Okay. We built our own tool as well for how do you take a shop person and interact with a modeling tool. That's what we did. So you can just be able to interact better with that. Visual twins for mining vehicles. The mining vehicles, they're pushing towards, I think it's level 9, which is almost autonomous, but if it encounters a problem, it must break itself. It must be able to defend it, protect itself, protect the environment. So that's a big robot, right? So our digital twin was, how do you start that process? How do you, what factors do you need to look at? What does your vehicle need to be able to counter, be able to handle, right? So there was a project that ran over 2 years that collected data. One of the Anglo mines provided the data, and you could see they gave us everything, GPS. It was a fully instrumented truck, and you could see how the guy brakes, how he accelerates, everything like that. And even when he starts cutting corners, because that GPS they had on there was really good, right? So from this data, then we could build models for these semi-autonomous trucks. Okay. So this is an ongoing project, and we are hoping that we will be involved in the next phase of actually dealing with the big truck and trying to get it to that stage of being able to protect itself. Getting back, I think I'll stop after this slide. Yeah, is if you introduce technology, a robotic system into a company, can that company actually absorb that technology? So the Future Production Group, they do what they call a 4-hour assessment, right? They go into the company and they spend about 2 days. I've been on the companies as well, and there's a whole lot of sections that you deal with, right? You interview the CEO, finance, HR, everything, right down to the person working on the floor. And these tools then can map out where you are, so this is where your company stands, and then through the conversations you say where you want to be. So you don't have to be fully 4-hour compliant, everything. For your company, where do you need to go? And then you develop strategies for them to move forward. Okay, so if you think about building robots, think about the end user and how they're going to actually get in and use them. Okay. I'll skip that pothole section. Okay, thanks. So we do a wide range of things, but we still have quite a lot of fun with the robotic side as well. I'll open it to the floor. Questions?
Hi, sorry. I would like to ask about the security platform robots. Have you considered other methods of powering it, considering the sustainability goals that we have, switching to fully electric or hybrid version of the propulsion system?
It's fully electric.
Fully electric?
Yes.
Right?
No, I think he just misspelled petrol.
Oh, is it?
It's
Yes, I mentioned
petrol.
yes, petrol. Okay, so I have an error. Yes,
thank you.
Yes, no. In the past, we did a lot of petrol, internal combustion engine robotic systems, right? They're a lot more harder to control, right? I mean, that electric is the way to go from a robotic system. If you can avoid going to an internal combustion engine, avoid it, like the plague. Yes, okay. Any other questions from the floor? Okay.
Sorry, you had a slide where you had the demo factory and things going on. Those cobots that you had, are those ones that CSR built, or do you buy externally?
They were Panda robots.
Okay. And in general, would you if you weren't doing something for a particular often manufacture your own?
It's like a pendulum for us. But sometimes we want to build, and then we will go along and build something, right? And then we go along into the phase of, no, we're going to buy, right? And we're in the we want to buy phase at the moment. We don't. It's all comes down to cost, right? Okay. So and who's funding it, right? So we did have a project where they wanted to see what is it going to cost to localize the robotic arm, right? But government said, what's it going to cost, right? You do a whole thing, and then we built, I think, 2 demo models of the thing, but they weren't bad, right? For the application they were looking at, right? It's low weight, pick and place kind of stuff, right? But companies, Fanuc, all those places, right? They will do it a lot cheaper actually than usually, right? It is more cost effective to rather buy those kinds of things. You must choose what you buy and what you do. Okay. And at the moment, it's cheaper just to buy that stuff. Okay. Here's your Cobot. Cobot has a whole lot of other playing toys inside there. You don't have to build yourself. Okay, cool.
Thank you. If you don't have any other questions, let's just put our hands together. I think we're going to go to Dr. Solomon Makinola, who is going to be giving his talk on remotely. Just get a small technical break. We were really told. I hope so.
Hello?
You want at least Dr. Kinola, I think we are ready for the presentation. And at the tail end of the presentation, Simbarashi would also be continuing. So come and carry on. Thank you.
The presentation I just gave to them. It looks like they want to go that route. So I've got the list of questions I want to do. It's just the tail end.
My findings. Now,
This isn't the audio that
hello? Okay, can you hear me?
We can hear you.
Oh, great. Thank you. I guess I lost.
Second, as we put you back on the screen, and then we can start.
Yes. All right. Great. I can see. Yes, I have a view of the team. Yeah, my presentation. Should I present from here or?
Yeah, you can go ahead from where you are.
You have the slides?
Yes, we have the slides, but you're welcome to present from where you are.
Okay. All right. Okay. That means I'll have to upload my slide. Okay, I have a colleague, a junior colleague with us at the meeting. His name is Simba. Simba, please, can you stand up for identification? He will be joining me in the presentation as we progress. Yes, all right. Good day, everyone. My name is Oluwole Akiola from the Institute for Intelligence System. I'm here with Simba from Technola. We're both from University of Johannesburg, and we'll be presenting some of our research within the purview of robotic communication. We'll just be covering a couple of things on the projects we've been doing, and as well as some of the projects we're doing at Institute for Intelligence Systems, as well as from Technolab. Basically, the Institute for Intelligence Systems is dedicated to, of course, driving the 4IR initiative. And so far, one of our major stream or idea is to utilize emerging technologies within robotics to teach, as well as to bring about solutions to some of the real life problems we are encountering in our world today. The first project, or one of the tools we have at our disposal, is called Spot. And Spot is sophisticated, agile mobile robot from Boston Dynamics. So Spot is a robot that can do a number of interesting tasks. And so far, we have incorporated it into a number of research areas. But I'll just be sharing two of the key areas that are very important for use. And also, Spot is it's a robot. So, of course, we can also use it for a number of demonstrations and tasks within the purview of learning how robots can be used within different spheres and for entertainment as well. So first and foremost is the area of mining. And we have a couple of engagement with some of the mining industry within the South African mining establishment. As we all are aware, mining is a capital intensive industry, and due to the challenges involved in the extraction process, the research process, we are engaging with a couple of mining industry to help with surveillance tasks, as well as detecting a number of challenges within the mining environment. So far, it's still an emerging research because the data is just coming in. We are still establishing some of the requirements to carry out the task due to the risk involved and the sensitivity or the nature of this project. But the focus, of course, is to ensure safety, efficiency, and cost-effective operations within the mining industry. And so far, we have two mining companies in South Africa that have engaged with the Institute for Intelligence System to carry out some of the tasks that is expected within the purview. The second area of interest is human language interaction through robotics. Of course, human-robot speech interaction is a very fascinating and interesting area, and it's really evolving as numerous research and studies have been conducted on human robotics communication through various means such as speech, vision, gesture, touch, emotion, and other signal cues that are very relevant within this sphere. So all these considerations are natural structure, especially within the space of human robotic interaction through speech, which is a common communication medium. As a result, voice recognition, which is a long-standing subject in literature, is a line of action we have considered to incorporate using, of course, very advanced tools within the deep learning framework and automatic speech recognition or speech processing system. But our focus is not on for all languages. We narrowed it down to specific indigenous African languages where it is few and evolving within the space of our African language, especially South African language, as a case study, where we select certain verbal cues that can be used as interaction mediums between the robot to give instructions and command. And this is very, very important, especially in cross-cultural studies, as well as within the service robust model guidelines. So as we are aware, of course, the industry of robotics, communication and engagement, language plays a significant role in acceptance within professional service robots. So the culture for acceptance in this industry is still evolving, and African languages, especially indigenous African languages, are a little lacking in terms of use cases and scenarios, and we are building models and systems that can engage in robotic communication to drive the narratives. Of course, some of the things we're doing is giving instructions to robots through some kind of multimodal command, especially speech, then allowing human interaction to do basic things that are necessary, at least for the start. Of course, natural language understanding is very critical with speech synthesis, from where the robot itself can communicate and relate and refer back from the response to give responses to various instructions that have been communicated. So to a large extent, we intend to create an effective speech command recognition system for selected indigenous African languages utilizing cutting-edge deep learning techniques. That is still in the pipeline, and I hope that by our next engagement, we should have a prototype and we can even demonstrate some of these tasks. And secondly, to improve performance by making the robot more accurate, flexible, and responsive to verbal cues. And of course, we know there are a lot of intricacies in language, especially with how speech, in terms of the speech recognition systems and the challenges therein. So these are some of the two of the main tasks we're doing. I'll hand over to Simba to give more instruction to give more talk on the Techno Lab and some of the other tasks that have been done at the University of Johannesburg in terms of in line of some of the research work we're doing. Simba, over to you. Hello?
And good afternoon. I was shaky after lunch. My name is Simba. Yeah, that's short of my full name. I'm an engineer by profession, but I'm not much of a researcher. I did up to masters in electrical and electronics engineering. Probably looking forward to do PhD with one of the supervisors here, potential. Our main focus at TechnoLab is we do outreach programs mainly to empower the communities with the new technologies. So it's more of community development through technology. So we introduce the community to 4 other technologies, the likes of the likes of 3D printing, VR, and then AR, and also Internet of Things. So how we do it is it depends on the target market. So all of our projects are fund based. So we approach corporate companies and say we are going to this society is disadvantaged in terms of how they're exposed to technology. Can you fund us on this type of project that we are trying to do? So our main focus area is mainly the coding and robotics part. That's why we are here, because it's a robotics thing. So what we do is there are many societies in South Africa, especially in the educational sector. They don't even know anything about technology. One of the questions that I always get asked is, what is a robot? To them, they know a robot is a traffic light. That's what they say every time when they are getting off a text after robot. So that's why they know. So as we go in those communities, we work with the Department of Education to locate the schools that are disadvantaged. Can you go to next? Right, so we go to schools that are disadvantaged, and then we create robotics club. So these programs started all the way from 2021 before the Department of Education tried to make it now a subject. So starting next year, coding and robotics will become a subject in primary school, high school, everywhere. So we were the first people to actually start doing this, running co-pilot with many schools, but mainly our targeted audience are schools that are in rural areas that have never heard of technology or anything. So what we do is we go to the Department of Education, some district probably in, right now we are focused in Northwest. So we go and look for schools that are in deep rural areas, and then they look for probably depend on the funding. So if the funder is willing to fund for 20 schools, we look for 20 schools, we bring their teachers for teacher training. So we train those teachers on the basics of programming and basics of robotics. What is a robot? Like the basic, what a robot is. From there, we teach them also programming. So programming mainly, if you look at the corner here, you see the type of language. So many of you are good with programming, but these guys, they don't know anything about programming. So we teach them from block-based programming, and then we did a bit of basics of text-based. So text-based, we don't go in deep. We just give them the background of how to read the program, so understanding the concept of programming. And then from there, they have to go to the robotics club. So these clubs, they run throughout the year, like an extra curriculum, like to those that did debate in high school, those clubs. So yeah, but it will be a robotics club. So we supply equipment, we give them snacks also because it's an after school. So we supply them snacks, those learners. So the robotics club will consist of 10 learners and 2 teachers. So we train the teachers to go train the learners. And then we prepare them for the end of year. We do a World Robotics Olympiad competition with the learners with those schools. So it's part of the Lego community, the World Robotics Olympiad. So we make sure by end of the year they are ready. We go do the judging. This year we have the competition in October. We'll go and do the judging. We also do a district competition where we bring the funder and the Department of Education also to come and also witness what the learners are doing. So mainly the learners we're dealing with here are grade 3s and grade 4s. So it's not grown-ups. So I'm used to standing in front of young learners. That's why I'm a bit shaky. So, go to the next. Right? Part of the program, we do school visits. We go to schools to make sure the teachers are actually implementing what we are teaching them. And the competition, everyone is happy. They win. They win gifts. You know, learners, they want to be motivated that way. So we try to make robotics fun to learners, and the same way to say robotics is applicable in every environment, in education or in any industry. Go next. Right. We also do in-house programs. So these ones, if you check, probably in the research, there are many women, but in engineering, there are very few women. In my class, we had like 2 girls that graduated in our time. So these programs are there to invite girls for winter camp. We house them. It's also funded based also. We house them and we teach them about engineering. And also our main thing is what? Coding and robotics. We do them 5 days where we go through different departments at UJ, and then they understand the good side of engineering. And also these learners, they also come from deep rural areas. So we pick them from different areas, and then we go through the week. And also we have other schools that come through that want a bit of background of what is coding and robotics. Right, so just a summary of what we cover. These are mainly our clients, mainly are the schools from foundation phase, intermediate phase, and senior phase. So we do content development for those learners, but our main focus is what? Coding and robotics. So we make robotics more simpler, more than what you guys are researching on. We look for modules. So let's say you have your own module in your lab that you want to test, you can come to us, we test it with our learners. And also we have private sector. So we also have an ABB robot that we train technicians from different industry on ROS, that software system, how to use it. And then we also have tertiary institutions. These ones are our learners at UJ. So we collaborate with RIS components. They supply learners with the equipment. So they submit their proposal of the project they want to do. We assess, and then we recommend to RIS component to supply them components and some winning prizes. And also science centers, if they are looking into coding and robotics, technology related. And also Department of Education is our main selling point because of this whole coding and robotics thing becoming a thing. As also part of the department of the government side, we are also focusing into 4R technologies. We are launching a 4R lab in Tata. So we are training 70 teachers right now on 4R technologies, digital competence, augmented reality, application in educational sector. Thank you.
Thank you, Simba. So we're open to questions.
Thank you for that talk. Any questions from the floor?
Oh, I was supposed to steal in front. So like what type of like robotic tasks do you, robotic exercises do you kind of like give those students? So the code using that block-based programming stuff, I assume that one is like a simpler one compared to Scratch. What type of exercises do they, like robotic tasks, do they code using that? Examples.
So we use Lego Spike Prime. It uses a bit of our Scratch language. And then we use Spike Essential. It uses lower language like icon-based. And also do some Arduino projects. I think the other thing I forgot to mention is we also run competition for high schools in collaboration with CETA, DSI, in coding and robotics, where we give them a topic, and then they write an essay. So some of your research topics, we actually see them from high school learners. No offense, but we also so we recommend them. We recommend them the equipment to use and the type of programming language. So we assign them mentors from varsity to help with the programming. Yes.
What has been the impact? How long have you been doing this? And like, do you kind of track what kind of difference you're making in terms of growing the robotics field?
The good side is it's becoming a subject. We're the one who started with it. The other side is we work with the Department of Education at UJ, where we have researchers that go do follow-ups in schools to see, does it have impact to learners in other subjects? Are they improving? Because we teach them logical thinking. So is there an impact also in other subjects? If there is any shaky thing, every year we sit down to improve from what we did from previous years. Yes.
The reason you specifically go with Lego, I know it's a lot more expensive. Like, would you consider transitioning to microbits, or what's been your experience with the different options for children?
So the reason why we stick with Lego is because you're trying to cover a big curriculum. So Lego gives you more option in terms of what you're going to do and the targeted audience. So younger learners, they're easier to work with building blocks. But the higher we go with high school learners, we do Arduino mainly. So microbit is becoming a new thing they are introducing in school. So we're starting with that next year.
Thank you. Do you have any other questions from the floor? Okay, thank you. Can we just put our hands together for Simba? Thank you very much for joining us, even if you I understand you're traveling. But thank you for taking the time to join us. And
Thank you.
But we will go into our coffee break, and then we'll go into the posters. Good. Thank you for the speakers.
Yeah, often you say.
Gooi de e-spray. I won't trust those people with the e-spray. I'm scarred with the spray.
Basically, this is a dead zone.
Yeah, I'm not going to. You're not using. It was actually cool. They just look at me very weirdly when I buy it. Like a blind.
And he kind of runs this program with Pradesh. It's very interesting, and we're hoping to get more universities involved, as Pradesh mentioned in his talk, so that we can compete on like provincial level before we go international. Thanks, guys.
Thank Jen for apologizing on my behalf for taking up this last session before you guys are free to go home and enjoy life. Yes, as was mentioned, my name is Brandon. I am now a faculty member here at WITS, and I'm going to be talking about RoboCup, my journey through RoboCup a little bit, how you can get involved, what it is, obviously, for many of you who might not know. So yeah. So the first one is obviously like, what is RoboCup? Well, it's an international conference slash competition slash science expo. Lots of different things go into RoboCup. But in essence, it was a competition that was developed with one goal in mind, and that was, can we further robotics? Can we develop new robotic solutions such that a lofty goal that we can beat professional soccer players, obviously playing soccer. We can beat them in many other facets of life, of course. So that was the goal, and they hoped that we could do this by 2050. That is coming up sooner than later, and there's obviously many things that still need to be achieved. I'm going to show you a few highlights of some of the competitions and what it's about. Okay. My personal story with RoboCup was sometime like 2018, 2019, when I was a student here at Wits, and I was invited to have like a lunch with Steve, Pravesh, Benji, some other people from Wits as well. And, I was like, oh, cool, nice little lunch to have, paid for and all that. And we started talking as, people do. And Benji said, I have this RoboCup idea thing. I don't know, would you be interested in running it? Benji was my supervisor at the time. So of course, I said no. I didn't, as I was speaking about it. So obviously I didn't. And, that's progressed. So I said yes. And then we built this team over many, many years. And I'm going to be talking about some of our progress on that. It was interesting to hear that some people have done RoboCup stuff in the past, but it sounds like it's died off as well. I last year definitely sent emails out to a few people fishing to see if there were any people. No one said anything. That was super encouraging, that's for sure. But yeah, okay. So let's move on to what RoboCup is. Steve, you guys try the other one? Or?
Try one more time.
Okay, so here's just a little video that I'm going to play in a second. Okay. Oh, okay, sorry, not on that one. This is a little marketing video that they made this year for RoboCup 24, which was in Eindhoven. So this is some of the highlights of Netherlands, some stadiums, if you're into that type of thing. Cars, they have a huge Philips factory as well. But, the main purpose was just to advertise robotics to a general population, okay? And again, here's some the videos that they put together from previous events, highlighting and revealing some of the leagues. And there's a spot type thing that are included in the competition, which I'm going to go into more detail now. So RoboCup started just focusing on soccer, very small scale as one does when they're starting something very difficult, very bold, and important. And now it's been expanded to all of these lovely different things here. There's RoboCup Industrial, Home, Rescue, Junior, and the main one, which is soccer. RoboCup Industrial is a lot of what you guys have been talking about in the last couple of weeks, right? Sorry, weeks, what am I saying? A couple of days. It's been a long couple of weeks. And the purpose of this league is can we build and design robots that can work in industrial factory settings? Can I pick and place different instruments? Can I interact with different knobs or switches or taps and something like that? And how most of these competitions work is that they'll be given a scenario that they have to essentially solve. And based on how well or the number of features in that scenario that they solve, then they get a mark, and you competing against all these lovely people from a massive variety of countries all across the globe. Another one is a little video that I'll show you now is Home, which is about robots that are there to help people. There were some things to do with amputees and that type of thing. It's a similar type of idea, but robots in the home. Okay, can we get a robot that fetches out a cool drink or something if I'm sick? Okay. But I'm going to play a little bit of the video, but not the whole video, just to give you the background in this particular league. Cool. So again, there's plenty of videos to play. And one of the good things about using multiple videos is I don't have to talk too much. So the next league is RoboCup Rescue. And that's focusing all around problems like disaster situations. Can we navigate environments or operate in environments where we don't want to send a human, right? So maybe there's an earthquake or there's fire or something like that. RoboCup rescues that environment. Okay, and again, some of this includes simulation, some of this includes real life testing. My personal background, I never did robotics for any sort of degree purposes or anything like that. I've just done robotics as a side thing. It's part of my research now, but I never did a PhD project on robotics or anything like that. I come from a very programming, AI, machine learning background, reinforcement learning as well. And one of the interesting jokes that we kind of contemplated or we spoke to some of the leagues was that it's very hard to apply RL in these types of environments because you can't have someone waiting on the phone, there's a fire and they're like, yes, I can do one of my rollouts on my robots. And then the firemen have to just wait okay, are you guys done so we can go rescue these people? But the RoboCup Rescue is this competition that is, designed such that we can try solve these problems in a lot more of a fun, less morbid type of environment. So this is just some highlights from last year's, not this year's, but you'll start to see. So how it works is that the competition will build these arenas, okay, that are difficult to navigate. As you can see here, they're all very oddly shaped, constructed out of jarring shapes and this type of thing. Sometimes they put gravel, doors, and the purpose is that can we navigate this environment again all autonomously, such that we can maybe pull a key out of one of these holes or open a door or a faucet or something like that, right? Maybe there's a gas leak and you need to turn something off. One thing that I should highlight for all of these leagues, which is maybe something slightly different to what we've been touching on so far, slightly different, some of the chats have been around this nature, is that its focus is on autonomous processing, right? These can be controlled remotely, like the telepersons type stuff, but the purpose of the competition is can we do this autonomously, without the intervention of a human controller? So it's just an example of one of those problem tasks, and you can see the students very frantically watching just outside of the camera shot. They're hoping that all their hard work has not been wasted. Cool. So that's RoboCup Rescue. What's this one's right? Junior. So what's very impressive or interesting coming from a South African perspective is when the first time I attended one of these events, you see these junior leagues and it's high school students. I'm like, geez, I wasn't doing this in high school. I walk in high school. But how they've integrated is quite cleverly. They'll do, line following, that type of thing. But even for lower grades, they'll have to, design some sort of show which has incorporated robotics, right? So they'll have very simple robots and maybe they do a dance around them and it's quite a fun experience. And again, these are young high school students competing at this cool international. So that's RoboCup Junior. And then the one that obviously most important to me is RoboCup Soccer. And even this league itself is subdivided into multiple different variations, and you can see some of the different examples of that. It's made up of standard platform, which are robots you can just purchase, okay, off the shelf, as well as human designed, many years of iteration exampple of robotics as well. So this is what I'm going to be talking to you guys mostly about today. Some more highlights. Again, I'm just basically here as a PR rep for competing in RoboCup because I think it's so cool. So I'm going to be showing some highlights of this year's iteration of the competition. And what I want you to just notice is all the varieties of leagues and experiences that you can have at this venue. as you could see there, like this was the highlights, I think, from day one. And this is a multi-day international yearly event. And then day one follows like everyone's coming together from lots of different countries. A lot of things are broken. And a lot of like these early parts of the week is about fixing these different things. So luckily, I compete in a simulation 3D league, so if my flash drive works, my flash drive works. I can just clone my repo once again, and we're good to go. So for me, it's a great time because I just get to walk around, do not so much looking at all these cool things. One of the things you might have seen there was that they had this robot that could write in like sand. And every morning, every time you come back to the events, like you would see this new like phrase or like moniker written out across the street. And then as the day progresses, like as the wind comes, it blows away. And then the next day, there'll be like a new motivational message. And then the other thing I want to highlight there is like, I think this year in particular, the organizers did a very good job of like including like children and the community, like the local, like public, right? What's really cool about this, as opposed to other conferences I've been to where it's something like this, and not that standing in front of people and speaking and hearing other people speak is the most boring thing in the world. But yeah, it's like very interactive, right? I mean, robotics is like already quite an interactive, science in itself. But they filled like the spaces with a lot of these more expo style things, okay, like that sand drawing robots. They also had like people from military and how they would speak a little bit about like their experience of how they like utilize robotics for like minesweeping and these types of things. They'll have like industry representatives as well demonstrating their new technology. And it's a really great venue or like event, I think, for robotics, purely because of this like networking aspect, as well as how fun they make it for like a wide range of people. So those are the highlight videos for day one. I'm going to show you like the following days now as well, where it starts to focus a little bit more on like the actual competition aspect. Okay, so the expo type thing happens every day, but the competition starts to really build up, and it becomes quite exciting. I think if you think to yourselves, and after watching that video, you would be very hard pressed, and perhaps come and tell me if you feel that any of the robotics that you have been doing wasn't like represented there, right? There was like drones, there's bipedal, tracked, quadrupedal. There was, leagues that focus specifically on running or walking and like the cheetah type stuff, perhaps. So there's like, having heard like all of your talks as well, like I can definitely see like, oh, in my mind. Note on the Rescue League, tracked robots are the one. Don't even try the quadruped stuff. It doesn't work very well. Like the bipedal, there's specific leagues for bipedal, like soccer leagues, right? So there's like a place for every one of our types of research at this venue. And then the last video I'm going to play, also at the end there, you saw like, it's also still a formal conference, right? People publish research at this venue. People present research as well. So, you know, it has literally everything, which makes it quite cool. And this last video is highlights from the last day. So you'll see some of the highlights of the final games. And, you know, this was at, it wasn't at a sports stadium hosted, but it was at like a sports academy. They really did well at making it like feel like an Olympic style event. So the stands were arranged very nicely, and you see a lot of public people there. The crowd really gets behind the different competitions, as well as the competitors themselves, right? It's their whole year's worth of work they've put in. So yeah, we'll see some of that. So as much as like we have supervisors that are, you know, super supportive when you're doing good work, you know, we don't have fans cheering us unless you do this, you know. Also on the note, Shane, that team called Romello with the full size bipedal and the robot fell over. I mean, if you've ever done work and you've seen a robot fall over, and you know, that's like super expensive equipment. But they're like the camera shattered across the field. And they have to like wheel it. Well, they carried it off the field. They didn't get a stretcher out or anything. They carried it off the field, and they put like a rod like through its like torso. There was a whole design for it. Did you see it like just planched up on the side? There was like a rod through it. It was very morbid. But yeah, they recovered, and they actually for the first time beat like the reigning champions in that division, which was really cool to see this like progression. Other things you saw at the end of the video was that, you know, they had humans playing against a medium-sized league is what it's called. And again, because that was the whole motivation behind this competition, or this whole competition, right? Is that one day we can beat professional players. You can see we're you know, not there yet. The people that were in that video or in the human team are like the delegates or like the founding fathers of this league. So they're not professional players. Peter Stone is one of them. He's not bad, actually. So yeah, he's pretty good. So perhaps if we can beat him, then we're close enough to beating a professional team. Yeah, so these are some of the highlights. Now I'm going to touch on like what I specifically do at RoboCup, which is in the simulation 3D environment. Again, I'm not like an engineer or something like that. I don't have that background. Would like to learn some of those skills. I come from a computer science background, and this is like the easiest entry point for myself, right? And most of the people from the lab which I come from, which is the rail lab, I didn't mention it at the beginning, but it was there if you saw the logo. That counts. Here you can see it's not the largest league. It's one of the smaller leagues, to be honest, in the whole competition. Not everyone was in this photo, but you can see like we had Pravesh speaking on Tuesday. That's him hiding over there. But yeah, so we compete in the simulation 3D environments, but this is, again, it's not like FIFA or something like that. When we say simulation, this is like an actual simulated version of a Now platform. Okay, so we've seen a few pictures of Nows from other speakers, but also in this video. You can see what it looks like on the left there. And the Now robot has like many degrees of freedom, right? I think it's like 22, around about 22 to 25, somewhere around there. Like, so we have like elbow, wrist, shoulder, ankle, lots of joints, all right? But because I have like this machine learning, like algorithmic background, like simulation is something I can handle that perhaps. How it works is that there's like a visualizer sure on the left hand side, but mainly it's this like client server communication, which is I'm sure what most people are very familiar with. The agent speaks to the server, sends its like effector or like velocity values for its joints. And then the server will process that information and send it back the perceptor values, right? And this is constant interaction over the whole game. And what you hope is that through some clever, intelligent cycling through these types of things, that your players walk and kick the ball and hopefully score. That's the whole point. Well, that is soccer. And so from my perspective specifically, this is like what the event looks like for us, right? There's multiple rounds. It's a league. It's a competition, like a World Cup. There's knockouts, there's group stages, all of those cool things. But what's also interesting is these other like sub-little challenges that each competition or league employs. Okay, like one thing that's been added recently is this ball throwing challenge. Okay, and then like picking up a ball and can we throw it? And that's very difficult, but it's like the next challenge in our league. So there's lots of these types of things, and that's what really helps like push things forward. Okay, there was a previous speaker who was saying like he's tired of this new people solving the same problems. Well, you see, because these students or these teams are associated around a particular competition, right? There's a joined like history. Okay, so the league looks completely different to when it started because there's this natural progression. Things are carried down. And what is very nice about the competition in general is that a lot of stuff is made open source as part of like the requirements in the league, right? If you're, especially from the winning teams or like the top competing teams, they have to like open the curtain a little bit and show what's behind such that new teams can help and like they don't have to start from scratch, which is really cool. And that's something we did, right? I didn't start from scratch. I didn't learn or build the perception pipeline. I didn't build the pipeline that communicates with the server. What was I interested in was I was interested in like learning low-level skills, like kicking, walking, using RL. So that's what I wanted to do, and I could do that, right? There was this freedom to do that because how available a lot of resources are. And as a result of that, not just me, but like there's a team of people, right? Small team, very small team, 3 people in total. We were able to win our first game against the Brazilian team. Brazil, famous for soccer, defeated the lowly South Africans. And yeah, you've seen this video actually in the introduction, but oops, I skipped ahead. Steve, this is the one video I needed your help. All right, thank you. Yeah. So Bahia Bati is a Brazilian team from. They told me it's the biggest university in Brazil, so I'll take their word for it. And this is a team that we have, come close to drawing with before, which is not like the greatest, sentiment to say. But finally, we were able to, be. And you'll see here that like robotics is still at its infancy, right? We're not the best team as well, so I'm going to show you a better looking. But there's a lot of falling over, a lot of collisions. RL safety, which is sure something is interested in. It's not really come to a robot. It is all about, can I learn like a better kick? Can I learn a faster walk? Getting up faster is even very important. And we were able to like develop this pipeline that allowed us to learn a kick finally, which was like a huge limiting factor for us. Now, one of the other leagues is called Fat Proxy, and it's this idea that like, okay, let's say everyone has the same low-level skills. What are the differences in our high-level strategy? It was, soccer or football, whatever you want to call it. It is a marriage between these two things, right? There's skills and then there's strategy, but that's much like any, complex domain, right? There's skills and strategy. But here, each of the skills is the same, like walking and kicking is somewhat the same across all the different teams. It's all about like who's more intelligent with choosing which skill to use when. And it turns out we were more intelligent, which is great against this Brazilian team. I am hiding the losses, of course, for storytelling purposes. But yeah, you can see here the kicking isn't like a natural kick. It's like a teleporter type thing. But it's like the decision-making process that we look at this test here, like questions on like, where should I be standing, right? What is an optimal formation? Who should I pass to? How do I navigate without colliding or the collisions happen as well? So here's just like the ending of this video where really his like behavior got confused and he walked away from the goal. But again, the important thing to realize here is this is autonomous, right? It's like hands off, no control. You type your code, you compile it, you send it, and then now you wait. And then hopefully they win, sometimes they lose. And each day you can actually update your code, which is quite nice. The other thing to understand here is that each of these agents is distributed the same code base, right? It's not like I programmed the goalkeeper there, like player one, to do something specific, like he has his own code base. There is intelligent decision-making, which we could, call if statements perhaps, at a level there where you are determining like who should be doing what, right? So not only is this a continuous action, continuous state problem, right, which is hard, it's also a multi-agent continuous action, continuous state problem at a high level at least. And that's what we like, right? We are computer scientists. We like machine learning and solving these types of things. Don't ask me too much about soldering and that type of thing. That's a lesser skill. Here's a video of the final, so you can really see how like the teams that have been competing in this league for many years, like over 10 to 15 years, like for us it's very new, have taken like RL, which is only really featured in the last recent couple of years, very far. Magma Offenburg, a team from Germany, has used like asynchronous PPO or RL, if you're not aware, to train a sprint that you run very quickly and then you try to slow yourself down as quick as possible as well. And maybe there's ideas from some of the talks earlier about maybe how to improve that approach because they have an issue of slowing down. And then the other team, FC Portugal, has learned a very impressive dribbling skill where they can maintain control of the ball loosely in between their legs and navigate past other teams quite efficiently. So here you can see like the end moments of a particular game or the final. It was 4-3 to FC Portugal. And we have a soft spot for Magma Offenburg because they've helped us a lot. So we're really hoping that they would win this year. Unfortunately, it was not to be. Sorry, Steve, can you please? So you can see a very like janky looking run, which is very inhuman, but very quick. And that is RL, right? So it will optimize some random thing that looks weird, but works. But FC Portugal's looks very natural and it's very controlled. And they have utilized this ability for a couple of years now to win the competitions. So that was like the final. It was interesting to watch from our perspective. Clearly, you can see we weren't in the final, so there's still room for improvement. And that's that idea of like room for improvement is what I'm going to lead on to a little bit now as like what we do to try and improve. And I'm going to highlight that by representing like RoboCup as a set of 3 challenges. Okay, there's the learning challenge, which is something we've been focusing on a lot. There's like the algorithmic or coding challenges as well. And of course, there's the engineering challenge that goes into it. In terms of learning, like it's all about these low-level skills, like multi-agent PPO, not done. It's too difficult, too complex a problem in continuous state, continuous action domains, especially when you have like 11 actors, right, versus another 11 actors. Multi-agent stuff is all like 2, which is very different. But it's like learning dribbling, standing, kicking. This is actually our one. Those aren't ours, but this is ours. So I'm proud of this one. You can ignore those. Like the approaches that we've taken over a couple of years is like from CMAES and simulated annealing, our genetic algorithm type approaches, to soft actor critic, PPO, like our reinforcement learning approaches. And it's somewhat agreed upon at the moment that like an asynchronous PPO, which is like highly parallelized version of PPO, is the only way to really learn like these really complex low-level skills. Even though it's like doable and we see great results, it requires a lot of like reward design. So if you've ever done oral, like this is like the most painful part of it. It's like, do we penalize if I fall or not? But then he just doesn't kick, he just stands because he's not falling. Do I reward velocities or distance? Do I design curriculums? Like, what do exactly I do? Like ages on this just for kicking. It was so demoralizing. And we built like complex learning or like reward functions, and then like those didn't even work. And then we started like retracting from that a little bit, and eventually we landed on this, and it was actually pretty good. So you add like the X distance, so just X, not the Y, because we want to kick kind of straight, which is important. The distance and the velocity of the ball. And we only calculate this or check this after 20 steps. If you do it after every step, it didn't work for some reason. RL sucks. And then we subtract the Y component because we want it to be, like I said, straight. All the spoilers. So what we got is these graphs, put these in papers so that people in your reviewers will say, oh yeah, okay, that's fair, good job. But what's cool is like you look at the kick actually in the simulator, right? But you can see we can now like kick like 15 units, which is like half the length of the field. The other part is like, well, okay, we can kick this maximal distance, but can we kick like determined distances, like intermediate ones? Like if I'm trying to pass, if he's not 15 units away, well, I'm kind of screwed if that's the only kick I have. So can we kick like X distance away from our current player? And we were able to do that for relatively good distances and across multiple different types of robots. So these are just some of our results. The thing I really want to highlight is that we built this training architecture, and it's available. You can go to the archive paper or download it off the repo. And it's like super. It took a long time to develop. But it's like, it becomes dead simple now. It's somewhat a gym environment. Like you create the environment, you create the agent, you tell it what type of learning agent it is, and then you say learn, and it's done. You are done now. So you can thank a colleague of mine, his name is Michael Buchman, for this whole infrastructure, which has really helped us a lot. And it works a little bit like this, that there's a start function, it creates the and the simulated environment uses something like called SimSpark. So, Gazebo, well, there's another thing called SimSpark. You create an RL agent, and it uses like stable baselines type of implementations for different RL algorithms. And then the last part, when you say learn, well, the server will send information to our like RL environment wrapper. That will send information to our RL agent, and that's the, your end.step type functionality. And that will work. And this is what you can just clone, and then you can train a kick just like that. So we feel this is a nice contribution. The other aspect that I'll touch on is like, it's a great domain for like algorithmic problems, right? We have recently introduced RoboCup in terms of like algorithms into our undergraduate courses, well, course rather, where they have to solve like an assignment problem. Who should go where, in essence. Some other things that we've done is like this formation pipeline, where we select like a base formation, okay, like 4-3-3. These are soccer terms, of course. I won't bore you on them. And then we calculate various heuristics that represent different components. Here, the color of this like heat map represents like how intense the signal is for a particular type of scenario or question you've been asked. So there's a threat map, perhaps, right, where we consider opponents to be threatening, and the trajectory towards our goal would also be threatening, right? Because they could kick along that path. So you can see that we've got code that kind of generates this heat map based on threat. Obstruction uses this Bresenham line drawing algorithm, and this is how we can like place players in positions that don't obstruct themselves from scoring the goal. So here you can see like these green circles, which are the opponents, are like obstructing certain other fields, certain other positions on the field. Cool. An openness map, if you want to score goals, you need to place players in open positions. So maybe design this openness map. And then the idea is like, okay, well, how can we combine these elements together to form different roles, like defenders, midfielders, attackers? Maybe they have different versions or different like realizations of these different maps. So you do that. This is like a designed approach, right? You select those. But you can use like maybe machine learning or some sort of optimization approach to weight how important these different maps are when you're combining them into like a combined map. This is future work that we haven't done yet, but it's something we are interested in. So you get these maps in the end, and now you have ideas of where your players should go. And this is a huge problem when it comes to soccer, right? Like managers have been dealing with this, like there's lots of different strategies. But how do you do this like algorithmically for your team that you can't control, right? I can't tell them to do things from the side of the field. I can't send them messages like that. So they have to do this on their own. The last step is just to identify the important locations. And how we do this is we just look for the reddest dot on the field. We add that to a position, and then we decay that dot, right? So we don't select it again. So we just do this for 11 players. So we take these, and now we have positions, these like different colored circles to go to. Cool. So this is just one example of like algorithmic problems in this space, just like there's many examples of like low-level skill learning problems in this space. What's super cool is what I like call side quests is that, again, at this competition, you can speak to so many people that can help you in lots of different ways to achieve problems in your own league, even though they're like maybe in rescue or something like that. For education, so I'm like an academic now, I guess. For educational purposes, there's a lot of these like educational robots that are also that are used for like teaching children like how robotics works. And this is something that I've been more and more interested in like finding out like why people choose to do engineering or computer science. People, how can we give them the opportunity to see these types of simple robots. And then, again, interacting with people from the other leagues is just like a huge benefit. This was like one of the finals for the now standard platform. We'd love to compete in this league, but it's expensive. These robots are quite expensive, even though you can get like discounts for universities. It's still a bit beyond us. But yeah. And then lastly, sorry, I'll pause it and then play it again now. This is the middle side leagues, and this is like the Premier League at the moment because it's like the closest realization of like a team that can beat professionals. This was even more important in Eindhoven because there's a university, in Eindhoven who competes specifically in this league, and they're the best at the league. So it was a good like home ground vibe. And here's just like a video of me like sitting in the stands watching it. What's also pretty cool because I'm an attendee, I can stand here. If I wanted to, and I do stand there a lot of the time. They're like courtside tickets, if you know that. So yeah, again, other leagues are super cool. Lastly, I just wanted to finish on like how to get involved. There's obviously a website. You can follow links. You can follow drop downs and click on all of them. Each league has a massive amount of resources, Discord channels, that type of thing. What's super nice about Simulation 3D is that there's a lot of repos for code bases, right? So you don't have to start from scratch. This first one here was released in 2023 by SC Portugal. It's amazing. I'm actually in the process of converting from our C++ code base into the Python code base, purely because it's so much better. Again, if you get hold of these slides, all these QR codes, hopefully work. The links are there. So yeah, I recommend using the SC Portugal code base. This would be like the Discord channel for our league specifically. These people are also fantastic. Likewise for all the other people in other leagues, I'm presuming. But like whenever we've had issues, like whenever I've chatted to these people, they were always very willing to help. Like if I had a problem and I described it, they would sit with me on a Discord call, obviously, and try to help me get through it. The other thing that Jen briefly mentioned is that we've been competing in this quite a while, but we only ever really get to test our mettle once a year when we go to these very very nice competition, obviously, but there's travel expenses, registration costs. It would be much nicer if there was some national league, although it sounded like that didn't work out for a lot of people. In maybe Africa, South Africa as well, where particularly in the Simulation 3D, where we can compete, and maybe form a stronger team going forward. If that's something that's interesting for you guys, please email me or chat to me now. I would be willing to help, organize something like that. The last thing that I didn't touch on was this engineering aspect. We face many engineering problems, stuff that I would call engineering problems, like communication with a server, or the refresh rate of our vision pipeline or something like that. Funny story, when we kick using our RL, the forward pass of our PPO model takes too long to process vision and kick. So we literally just don't process vision while we're kicking. So you're just okay. After we get into a position where we think that's where the ball is, at least. But these are the engineering problems that I would classify as engineering problems. But I know that's a different take on engineering. What we're more and more getting interested in is perhaps one day competing in one of these other physical leagues. So I'm looking at how we could get involved. Me, Pravesh, and some of the other people in specifically the small size league at the bottom left there. However, this is just something that we think is maybe the most appropriate league for our knowledge. But if we form maybe a collaboration, maybe one of these other ones is more appropriate. And here it's just a summary of the variety of physical robot leagues in RoboCup. So there's what we call adult full size. So these come to here. Okay, so they're quite big. I don't know what this one is. That's marketing. There's teen sizes and these kid sizes all the way down, to the ones that are your shin height. And so it's quite daunting for us because we have no real experience with these types of true engineering problems. So again, if this is something, hopefully maybe I've enticed you enough that you guys are interested in, please have a chat with me. Or at least tell me where I could buy something that looks like that. All right. Yeah, that is it from my talk. Thank you very much. I know it's been a long one. Good job. Are there any questions if there is time? Yes, yes.
Quick one. So the guys that are using the Now robot, do you know if they've kind of put their own firmware on it? Because UCT has a Now. We've had it for probably about 10 years now. And in the intervening time, the company that makes them went under and all the forums disappeared and got scrubbed. So I have a bricked Now.
I see. So from my understanding, therefore backlighting, from my experience, the only limitation they have is that they can't physically change the components of the robot. Okay. They do sometimes tie the hands behind the back and tape on the feet and stuff like that. But otherwise, all they do is change code as well as firmware. So yes, if you needed help on that, I'm sure one of them would be available.
I know a slightly more technical question. Why is it that everyone uses RL and no one uses more white box or model-based planning methods?
So again, it's not that they don't actually. It's been a progression. That's what was used all the time. like walk cycles, all of these types of things, forward kinematics, inverse kinematics. Like the backbone of our thing is actually inverse kinematics. These are still utilized, but they're seeing that more and more RL is just better in simulation. There are no deployments of RL for like complete low-level skill solutions in the physical leagues. For certain aspects of it, they use RL for optimization purposes, but not for like, oh, I want to train a walk now. But in simulation, it's more and more becoming like machine learning based, really, because it's better. Unfortunately, you have a particular bone on it. Any other questions? Yes.
So it's really cool what you're doing. So the simulator version of this game, can you transfer some of it to the real world, or have you tried some?
Yes. So the whole, again, I didn't touch on this well enough, I think, but the whole idea of the league, again, is that we as an entire community push forward to beat humans, right? Not that the middle size has to beat humans. But the idea is that, simulation leagues should learn like these low-level skills that then can be transferred onto their physical counterparts. Like that's why there's a simulated now review and then there's an hour robot, right? That's a very obvious gap. So that is the design intent behind the competition, definitely. It's not done, I would say, as much as it should be. Again, like Sharu mentioned on the very first day, that there's these differences between the simulation and the real world, which are still hampering that type of progression.
And the RoboCop simulator can very well fit the definition of a low fidelity simulator. It is like, it's a very bad simulator, physics simulator.
Yeah, it's got a lot of noise and there are issues, but these just make it a more like complex environment. I mean, the world has noise as well. Maybe it's the most high fidelity.
So high fidelity in terms of complexity.
Yeah. Any other questions? Yes.
How do you get invited to compete? Do you have to meet like a minimum requirement?
So there are qualification requirements. Each league is different. The physical leagues, you have to like submit video evidence that your robots can do certain things, like kicking or walking or moving or something like that. For our league, you literally submit your binary. They play it against the team. They being like the committee, the league's committee. And then based on that, you will qualify or not qualify. So there's like a call at the beginning of the year for qualification, and then you get your
The peer review is a bit more objective.
Yeah, it's also not blind. The people who are doing the reviewing are people that you've probably met and competed with before as well. However, like there's not so much a limitation of like qualifying is easier than getting a paper published. Definitely, these teams, the leagues want new people to compete, right? And they're super supportive with new teams specifically because they know that's going to help the league grow as a whole, right? This longevity of the league. So we've seen in like some of the physical leagues where teams come with like even a few robots, and then it's just that the fact that they came there to meet the rest of the community that then they can go forward and do better. So it is quite a nice like community environment, I would say. Cool. Well, thank you, everyone.
I don't know.